sklearn, linear model. Description. The sklearn, linear model module in scikit-learn provides a collection of linear models for regression and classification. Linear models are a powerful and widely used class of machine learning algorithms, known for their interpretability and efficiency. Inputs. X a 2D array representing the feature matrix, where each row represents a data point and each column represents a feature. Y a 1D array representing the target variable for regression or classification problems. Outputs. Model and instance of the trained linear model, containing the learned parameters. Predictions. The model's predictions for new data points. Steps. Model selection. Choose the appropriate linear model based on the problem type, regression or classification, and the characteristics of the data. Model training. Fit the chosen linear model to the training data X, Y to learn the parameters that best describe the relationship between features and target. Model prediction. Use the trained model to make predictions on unseen data. Metrics. R² R2 for regression measures the proportion of variance in the target variable explained by the model. Mean squared error MSE for regression calculates the average squared difference between predicted and actual values. Accuracy for classification represents the percentage of correctly classified instances. Precision and recall for classification measure the model's ability to correctly identify positive and negative instances. Visualization plots. Scatter plots for regression visualize the relationship between features and target variable. Residual plots for regression analyze the difference between predicted and actual values to assess model fit. Confusion matrices for classification show the number of correctly and incorrectly classified instances. Fine-tune parameters. Regularization strength alpha or C controls the strength of regularization to prevent overfitting. Penalty type L1 or L2 specifies the type of regularization to apply. Solver defines the optimization algorithm used for model training. Uncertainty methods. Confidence intervals for regression estimate the range of possible values for predictions. Prediction probabilities for classification provide probabilities for each class prediction. Challenges and fixes. Challenge 1. Overfitting. The model performs well on the training data but poorly on unseen data. Sample use case that resulted in challenge 1. Training a linear regression model on a dataset with a high number of features and limited data points. Fixes to challenge 1. Regularization. Add a penalty to the model's complexity to reduce overfitting. Feature selection. Remove irrelevant or redundant features. Cross-validation. Split the data into training and validation sets to evaluate model performance and tune hyperparameters. Challenge 2. Multicollinearity. Features are highly correlated, making it difficult to estimate model parameters reliably. Sample use case that resulted in challenge 2. Using a dataset with features like height and weight, which are naturally correlated. Fixes to challenge 2. Feature selection. Remove highly correlated features. Regularization. Apply L1 or L2 regularization to reduce the influence of correlated features. Principal component analysis. PCA. Reduce dimensionality by transforming features into a smaller set of uncorrelated components. Challenge 3. Data scaling. Features have significantly different scales, affecting model performance and parameter estimates. Sample use case that resulted in challenge 3. Using a dataset with features like income in thousands and age in years, which have different scales. Fixes to challenge 3. Standardization. Transform features to have zero mean and unit variance. Normalization. Rescale features to a common range, typically between 0 and 1. Challenge 4. Nonlinear relationships. The relationship between features and target is not linear, resulting in inaccurate predictions. Sample use case that resulted in challenge 4: using a linear model to model a relationship that is best described by a polynomial or other nonlinear function. Fixes to challenge 4. Feature engineering. Create new features that capture nonlinear relationships. Nonlinear models. Consider using nonlinear models like polynomial regression or support vector machines. Challenge 5. Outliers. Extreme values in the data can significantly influence model parameters and predictions. Sample use case that resulted in challenge 5, including data points with unusually high or low values in the dataset. Fixes to challenge 5. Data cleaning. Remove or correct outliers. Robust methods use linear models that are less sensitive to outliers, such as robust regression methods. Regularization. Apply regularization to reduce the influence of outliers. sklearn, linear model, logistic regression. Description. A logistic regression model is a statistical method used for binary classification problems. It predicts the probability of an instance belonging to a specific class 0 or 1 based on the input features. The model uses a sigmoid function to map the linear combination of features to a probability between 0 and 1. Inputs. X. A 2D array-like structure representing the features independent variables of the training data. Each row corresponds to an instance, and each column represents a feature. Y. A 1D array-like structure representing the target variable dependent variable of the training data. It should contain the corresponding class labels 0 or 1 for each instance in X. Outputs. Self returns the fitted logistic regression object itself. This object can then be used for making predictions on new data. Core. A 2D array representing the coefficients of the linear model. Each row corresponds to a feature, and the values represent the weight associated with that feature. Intercept. A 1D array representing the intercept of the linear model. Steps. Initialize the logistic regression model with desired hyperparameters, e.g., regularization strength. Solver. Fit the model to the training data X, Y by calling the fit method. This step involves finding the optimal coefficients weights that minimize the loss function, e.g., log loss. Use the fitted model to make predictions on new data by calling the predict method. This method predicts the class labels 0 or 1 for each instance in the new data. Metrics. Accuracy. The proportion of correctly classified instances. Precision. The proportion of true positive predictions out of all positive predictions. Recall. The proportion of true positive predictions out of all actual positive instances. F1 score. The harmonic mean of precision and recall. AUC area under the ROC curve, a measure of the model's ability to distinguish between classes. Visualization plots. ROC curve plots the true positive rate against the false positive rate at various thresholds, providing insight into the model's performance. Precision recall curve plots the precision against the recall at various thresholds, highlighting the trade-off between these metrics. Fine-tune parameters. Penalty. The type of regularization to apply, e.g., L1, L2, elastic net, none. Regularization helps prevent overfitting by penalizing large coefficients. See the inverse of the regularization strength. A lower value of C corresponds to stronger regularization. Solver. The optimization algorithm used to find the coefficients, e.g., LibLinear, Newton CG, LBFGS, SAG, Saga. The choice of solver can affect the speed and accuracy of the model. Maxiter the maximum number of iterations for the solver to run. Toll the tolerance for the optimization algorithm to stop. Uncertainty methods. Confidence intervals can be calculated for the predicted probabilities using techniques like bootstrapping or Bayesian inference. Prediction intervals can be constructed to provide a range of possible outcomes for predictions. Challenges and fixes. Challenge 1: overfitting the model may perform well on the training data but poorly on unseen data. Sample use case that resulted in Challenge 1: training a logistic regression model on a small dataset with many features may lead to overfitting, where the model learns the training data too well and fails to generalize to new data. Fixes to Challenge 1. Regularization: use L1 or L2 regularization to penalize large coefficients and prevent overfitting. Feature selection: remove irrelevant or redundant features to reduce the model's complexity and improve generalization. Cross-validation: use techniques like k-fold cross-validation to evaluate the model's performance on unseen data during training and select the best hyperparameters. Challenge 2: data imbalance: when one class is significantly more prevalent than the other, the model may favor the majority class and perform poorly on the minority class. Sample use case that resulted in Challenge 2: training a logistic regression model to detect fraud, where fraudulent transactions are rare compared to legitimate transactions, may result in the model being biased towards predicting legitimate transactions. Fixes to Challenge 2. Oversampling: increase the number of instances of the minority class by replicating them or generating synthetic instances. Undersampling: reduce the number of instances of the majority class by randomly removing instances. Class weighing: assign different weights to the classes during training to give more importance to the minority class. Use specialized algorithms: consider using algorithms designed for imbalanced datasets, such as smooth synthetic minority oversampling technique or cost-sensitive learning. sklearn, linear model, logistic regression CV. Description: logistic regression CV implements logistic regression with L1 and/or L2 regularization. It searches for the optimal regularization parameter C using cross-validation. This class is a wrapper around logistic regression that performs cross-validation to find the optimal C parameter. Inputs: X. This is a n samples, n features array, where each row represents a data point and each column represents a feature. It represents the independent variables or features used for training the model. Y. This is a n samples array, where each element represents the target variable or the class label for each data point. It represents the dependent variable or the class labels associated with each data point in X. Outputs: Core. This is the n classes, n features array, where each row represents a class and each column represents a feature. It stores the learned coefficients for each feature for each class. Intercept. This is a n classes array, where each element represents the intercept term for each class. It stores the bias term for each class. Steps: the logistic regression CV constructor takes several parameters, including C's, the values of C to be used for cross-validation. This is a list or array of possible regularization strengths to explore during the search for the best parameter. CV, the number of folds to be used for cross-validation. This determines the number of splits to be created when evaluating different C values. Scoring, the scoring function to be used for cross-validation. This defines the metric used to evaluate the performance of the model for different C values. Solver, the optimization algorithm to be used for solving the logistic regression problem. This parameter determines the method used to find the optimal coefficients and intercept. When fit is called, logistic regression CV performs cross-validation for each value of C. For each fold, the model is trained on the remaining folds and tested on the current fold. The cross-validation scores are used to select the best value of C. This involves choosing the C that leads to the best performance based on the chosen scoring metric. The final model is then trained on all of the data using the best value of C. Metrics. Accuracy. This metric measures the proportion of correctly classified data points. It's calculated as the number of correctly classified instances divided by the total number of instances. Precision. This metric measures the proportion of correctly classified positive instances among all instances predicted as positive. It's calculated as the number of true positives divided by the sum of true positives and false positives. Recall. This metric measures the proportion of correctly classified positive instances among all actual positive instances. It's calculated as the number of true positives divided by the sum of true positives and false negatives. F1 score. This metric combines precision and recall into a single value. It's the harmonic mean of precision and recall, providing a balanced measure of the model's performance. AUC. This metric measures the area under the receiver operating characteristic ROC curve, which plots the true positive rate against the false positive rate. It reflects the model's ability to distinguish between positive and negative instances. Visualization plots. Confusion matrix. This visualization presents a table that summarizes the performance of a classification model by showing the number of correctly and incorrectly classified instances for each class. ROC curve. This plot shows the true positive rate against the false positive rate for different threshold values. It helps visualize the trade-off between sensitivity and specificity, providing insights into the model's ability to discriminate between classes. Precision recall curve. This plot shows the precision against the recall for different threshold values. It helps visualize the trade-off between precision and recall, particularly in situations with imbalanced data. Fine-tune parameters. See the inverse of the regularization strength. A smaller value of C specifies stronger regularization. It controls the trade-off between overfitting and underfitting. Penalty. The type of regularization to be applied. L1 applies L1 regularization lasso, leading to sparse solutions, while L2 applies L2 regularization ridge, leading to smoother solutions. Solver. The optimization algorithm used to find the optimal coefficients and intercept. LibLinear is efficient for small datasets. LBFGS is suitable for larger datasets. And SAG is efficient for large datasets with many features. Multiclass. The strategy to handle multiple classes. OVR uses 1vs REST for multi-class classification, while multinomial uses a multinomial logistic regression model. Uncertainty methods. Confidence intervals. The confidence intervals around the predicted probabilities can be calculated to quantify the uncertainty in the predictions. This provides an indication of the reliability of the model's output. Challenges and fixes. Challenge 1. Overfitting. This happens when the model learns the training data too well, resulting in poor performance on unseen data. Sample use case that resulted in challenge 1. If the model is trained on a small dataset with many features, it might overfit to the training data and perform poorly on new data. Fixes to challenge 1. Increase the size of the training data. This helps to reduce overfitting by providing the model with more data points to learn from. Use regularization techniques. Techniques like L1 and L2 regularization can be applied to penalize complex models and prevent overfitting. Use cross-validation. This technique helps to estimate the model's performance on unseen data and identify overfitting. Challenge 2. Data imbalance. This occurs when the classes in the target variable are not equally represented, leading to biased model predictions. Sample use case that resulted in challenge 2. If the dataset has significantly more instances of one class than another, the model might favor the majority class, leading to poor performance for the minority class. Fixes to challenge 2. Oversampling. This technique involves increasing the number of instances of the minority class by creating duplicates or synthetic samples. Undersampling. This technique involves reducing the number of instances of the majority class. Weighted sampling. This technique assigns different weights to different classes during training to account for the class imbalance. Challenge 3. Choosing the right hyperparameters. Finding the optimal values for hyperparameters like C, penalty, and solver can be challenging and require experimentation. Sample use case that resulted in challenge 3. Different hyperparameter values can lead to different model performance, and selecting the best values often involves trial and error. Fixes to challenge 3. Grid search. This technique involves evaluating the model with a range of hyperparameter values and choosing the combination that yields the best performance. Random search. This technique involves randomly sampling hyperparameter values from a predefined range and selecting the best combination. Bayesian optimization. This technique uses a Bayesian approach to intelligently explore a hyperparameter space and find the optimal values. Challenge 4. High dimensionality. If the dataset has a large number of features, the model may become complex and prone to overfitting. Sample use case that resulted in challenge 4. When dealing with high-dimensional datasets, the model may struggle to generalize well to unseen data. Fixes to challenge 4. Feature selection. This technique involves identifying and selecting the most relevant features, reducing the dimensionality of the dataset and improving model performance. Feature extraction. This technique involves transforming the original features into a smaller set of features that capture the most important information, reducing dimensionality and enhancing generalization. Regularization techniques like L1 and L2 regularization can help to reduce the influence of irrelevant features and mitigate overfitting in high-dimensional datasets. Challenge 5. Computational complexity training. Logistic regression (CV) can be computationally expensive, especially with large datasets and multiple values of C. Sample use case that resulted in challenge 5. When dealing with large datasets and a wide range of C values, the cross-validation process can take a significant amount of time. Fixes to challenge 5. Use parallel processing. This technique distributes the computational workload across multiple cores, reducing the overall training time. Use efficient solvers. Selecting an efficient solver, such as SAG, can speed up the training process, especially for large datasets. Reduce the number of C values. Limiting the number of C values used for cross-validation can reduce the computational burden without significantly affecting the performance. sklearn, linear model, passive-aggressive classifier. Description. The passive-aggressive classifier is a linear model that uses an online learning algorithm to iteratively update its weights based on the misclassified instances. It's particularly suitable for large datasets where the data arrives in batches or sequentially. Inputs. X. The input features. Typically a 2D array where each row represents a data point and each column represents a feature. Why the target labels? A 1D array corresponding to the classes of each data point in X. Outputs. The fitted classifier object, capable of making predictions on new data. The trained model's weight vector, representing the importance of each feature in the decision boundary. Steps. Initialization. The model starts with initial weights, usually zeros. Iterative updates for each training sample. Prediction. The model predicts the class label based on the current weights and input features. Error calculation. If the prediction is wrong, the model calculates the error. Weight update. The weights are updated based on the error and the learning rate. The update is done in a passive-aggressive manner, meaning that the weights are only adjusted if the prediction was wrong, and the adjustment is proportional to the error. Metrics. Accuracy. The proportion of correctly classified instances. Precision. The proportion of correctly predicted positive instances out of all instances predicted as positive. Recall. The proportion of correctly predicted positive instances out of all actual positive instances. F1 score. The harmonic mean of precision and recall, providing a balanced measure of performance. Visualization plots. Decision boundary. A plot visualizing the separation line or hyperplane learned by the model, showing how it distinguishes between different classes. Feature importance. A plot depicting the magnitude of the weights assigned to each feature, highlighting their relative importance in the model's decision-making process. Fine-tune parameters. See the penalty parameter, controlling the strength of the regularization. A higher C value indicates less regularization, potentially leading to overfitting. Fit intercept. Whether to include an intercept term in the model. It's generally recommended to include it, as it allows for a better fit. Loss. The loss function used for training. Hinge is the default and suitable for binary classification, while squared hinge can be used for multi-class problems. Maxiter. The maximum number of iterations for the training process. Uncertainty methods. Confidence scores. The model can provide confidence scores for its predictions, indicating the likelihood of each class. This can be helpful for quantifying uncertainty and making informed decisions. Ensemble methods. Combining multiple passive-aggressive classifier instances with different random initializations or hyperparameters can provide better generalization and robustness. Challenges and fixes. Challenge 1. Overfitting. The model might overfit the training data, resulting in poor generalization performance on unseen data. Sample use case. When the training data is noisy or has a high dimensionality, the model might learn to perfectly classify the training data but fail to generalize to new data. Fixes. Regularization. Use the C parameter to control the strength of regularization, preventing the model from becoming too complex. Feature selection. Select only the most relevant features for training, reducing the dimensionality and preventing overfitting. Early stopping. Monitor the model's performance on a validation set and stop training when performance starts to degrade. Challenge 2. Sensitivity to outliers. The model can be sensitive to outliers in the data, which might significantly affect its decision boundary. Sample use case. In datasets with outliers, the model might be heavily influenced by these outliers, leading to incorrect predictions and a skewed decision boundary. Fixes. Data preprocessing. Remove or transform outliers using techniques like robust scaling or outlier removal algorithms. Robust loss functions use loss functions that are less sensitive to outliers, such as Huber loss. Ensemble methods. Combining multiple models can reduce the impact of outliers by averaging their predictions. sklearn Linear model, perceptron. Description. The perceptron is a linear model for binary classification. It learns a hyperplane that separates the data into two classes. It is a simple and efficient algorithm. But it is sensitive to the scaling of the features and can be prone to overfitting. Inputs. X the training input samples. It should be a 2D array of shape n samples. N features. Where n samples is the number of samples and n features is the number of features. Y the target values. It should be a 1D array of shape n samples. Where n samples is the number of samples. The values in Y should be either 1 or -1, representing the two classes. Outputs. Core the weights assigned to the features. It is a 2D array of shape n features. 1. Where n features is the number of features. Intercept the bias term. It is a 1D array of shape 1, which is a scalar value. Knitter the number of iterations the algorithm ran. Steps. The algorithm starts with a random set of weights. For each training sample, it calculates the weighted sum of the features. If the weighted sum is greater than or equal to the threshold 0 in this case, it predicts a class of 1. Otherwise, it predicts a class of -1. If the prediction is incorrect, it updates the weights by adding the features of the misclassified sample to the weights if the prediction was -1, or subtracting them if the prediction was 1. The algorithm repeats these steps until the weights converge or a maximum number of iterations is reached. Metrics. Accuracy: the percentage of correctly classified samples. It is calculated as the number of correctly classified samples divided by the total number of samples. Precision: the percentage of correctly classified positive samples. It is calculated as the number of true positive samples divided by the sum of true positive and false positive samples. Recall: the percentage of positive samples that are correctly classified. It is calculated as the number of true positive samples divided by the sum of true positive and false negative samples. F1 score: the harmonic mean of precision and recall. It is calculated as 2 precision recall. Visualization plots. Decision boundary: a plot that shows the hyperplane learned by the algorithm. The hyperplane separates the data into two classes. Confusion matrix: a table that shows the number of true positive, true negative, false positive, and false negative samples. Fine-tune parameters. Penalty: the penalty term to be added to the loss function. It can be L1, L2, or elastic net. The default is L2. Alpha: the regularization parameter. It controls the strength of the penalty term. The default is 0.0001. Fit intercept: whether to fit an intercept term. The default is true. Maxiter: the maximum number of iterations to run the algorithm. The default is 1000. Toll: the tolerance for the stopping criterion. The default is 1e-3. Shuffle: whether to shuffle the training data before each iteration. The default is true. Random state: the random seed used to shuffle the training data. The default is none. Uncertainty methods. Confidence score: the confidence score is the probability of the predicted class. It is calculated as the output of the sigmoid function, which is a function that maps a real number to a probability between 0 and 1. Challenges and fixes. Challenge 1: overfitting. The perceptron can overfit the training data, especially when the data is noisy or the number of features is large. Sample use case that resulted in Challenge 1: training a perceptron on a dataset with a small number of samples and a large number of features. Fixes to Challenge 1: regularization, cross-validation, and early stopping. Challenge 2: sensitivity to scaling. The perceptron is sensitive to the scaling of the features. If the features have different scales, The algorithm may favor features with larger scales. Sample use case that resulted in challenge 2 training a perceptron on a dataset with features that have different scales. For example, one feature is in meters and another feature is in kilometers. Fixes to challenge 2 feature scaling techniques, such as standardization or normalization. Challenge 3 nonlinear data. The perceptron is a linear model, so it cannot learn nonlinear decision boundaries. Sample use case that resulted in challenge 3 training a perceptron on a dataset with a nonlinear decision boundary. For example, a XOR dataset. Fixes to challenge 3 use a nonlinear model, such as a support vector machine SVM with a kernel, or a neural network. sklearn, linear model, ridge classifier. Description. Ridge classifier is a linear model for classification that adds a regularization term to the loss function. This regularization term is the squared magnitude of the weight vector. This forces the model to have smaller weights, which can help prevent overfitting. It is particularly useful when the number of features is large or when the features are highly correlated. Inputs. X the training input samples. It should be a 2D array of shape n samples. N features. Y the target values. It should be a 1D array of shape n samples. Outputs. Self the fitted ridge classifier object. Coa the coefficients of the linear model. It is a 1D array of shape n features. Intercept the intercept of the linear model. It is a float. Steps. The ridge classifier model learns a linear function that tries to separate the data points into different classes. It uses the L2 regularization term ridge penalty to prevent overfitting by shrinking the coefficients towards 0. The regularization strength is controlled by the alpha parameter. It calculates the optimal coefficients using a closed-form solution that involves solving a linear system of equations. Metrics. Accuracy. It measures the proportion of correctly predicted samples out of the total samples. Precision. It measures the proportion of correctly predicted positive samples out of all samples predicted as positive. Recall. It measures the proportion of correctly predicted positive samples out of all actual positive samples. F1 score. It is the harmonic mean of precision and recall, providing a balanced measure of model performance. Visualization plots. Decision boundary plot. It visualizes the decision boundary learned by the ridge classifier model, showing how it separates the different classes. Feature importance plot. It shows the importance of each feature in the classification model, helping understand which features are most influential. Fine-tune parameters. Alpha. It controls the strength of the L2 regularization. A higher alpha value leads to stronger regularization and smaller coefficients. Solver. It specifies the algorithm used to solve the optimization problem. Options include SVD, Kolsky, SAG, Saga and SparseCG. Fit intercept. If true, it calculates the intercept of the linear model. If false, it assumes the intercept is 0. Random state. It controls the randomness in the optimization algorithm if stochastic solvers are used. It is useful for reproducibility. Uncertainty methods. Confidence intervals. It can be used to estimate the uncertainty in the model's predictions by calculating confidence intervals for the predicted probabilities. Challenges and fixes. Challenge 1. Overfitting when the data is high-dimensional or has highly correlated features. Sample use case. A dataset with 1000 features and 100 samples where some features are highly correlated. Fixes. Increase the alpha value to enforce stronger regularization and shrink the coefficients. Use feature selection techniques to reduce the number of features. Challenge 2. Choosing the optimal alpha parameter. Sample use case trying to find the best alpha value for a specific dataset. Fixes. Use cross-validation to evaluate the model performance for different alpha values and select the one with the best performance. Utilize grid search or random search to systematically explore different alpha values. Challenge 3. Slow training time for large datasets. Sample use case training a rich classifier model on a dataset with millions of samples and features. Fixes. Use a stochastic solver such as SAG or Saga, which are faster for large datasets. Consider using a more efficient implementation of rich classifiers such as the one provided by Scikit-learn's SGD classifier with the L2 penalty. sklearn, Linear Model, Rich Classifier CV. Description. Rich Classifier CV implements rich regression with built-in cross-validation to choose the best regularization strength alpha. This is particularly useful when dealing with high-dimensional datasets where overfitting is a concern. Inputs. XA2D array representing the training features. Each row represents a data point, and each column represents a feature. YA1D array representing the target labels corresponding to the training features. Outputs. Core A1D array containing the coefficients of the fitted ridge model. Intercept. The intercept of the fitted ridge model. Steps. 1. Splitting the data. The data is split into multiple folds using a cross-validation strategy like K-fold. 2. Fitting models. A separate ridge model is trained on each fold, with different values of alpha regularization strength. 3. Cross-validation score. The performance of each model is evaluated on the remaining folds using a metric like accuracy or F1 score. 4. Best alpha selection. The value of alpha that yields the best average cross-validation score is chosen as the optimal regularization strength. 5. Final model. The final ridge model is trained on the entire dataset using the chosen alpha. Metrics. Accuracy. Percentage of correctly classified instances. F1 score. Harmonic mean of precision and recall. Measuring the balance between classifying positive instances correctly and avoiding false positives. AUC area under the ROC curve measures the overall performance of the classifier, considering both true positive and true negative rates. Visualization plots. Learning curve plots the model's performance, e.g., accuracy against the training set size. Feature importance plot shows the relative importance of each feature in the model. Coefficient plot visualizes the magnitude and direction of the coefficients learned by the model. Fine-tune parameters. Alpha is a list of alpha values to try during cross-validation. CV the number of folds for cross-validation or a cross-validation generator. Scoring the evaluation metric used for cross-validation, e.g., accuracy, F1, ROC, fit intercept, whether to calculate the intercept or not. Uncertainty methods. Confidence intervals. Compute confidence intervals for the model's coefficients, providing a measure of uncertainty in the learned values. Bootstrap aggregating. Bagging. Train multiple ridge models on different bootstrap samples of data and average their predictions, reducing variance and providing uncertainty estimates. Challenges and fixes. Challenge 1. Overfitting occurs when the model performs well on the training data but poorly on unseen data. Sample use case that resulted in challenge 1. A small dataset with a high number of features may lead to overfitting. Fixes to challenge 1. Increase the regularization strength alpha to penalize complex models and reduce overfitting. Use cross-validation to choose an optimal alpha value. Challenge 2: high dimensionality can lead to poor performance if the number of features is significantly larger than the number of data points. Sample use case that resulted in challenge 2: a dataset with thousands of features and only a few hundred data points. Fixes to challenge 2: feature selection techniques can be used to identify the most relevant features before training the ridge model. Dimensionality reduction techniques like principal component analysis (PCA) can be applied to reduce the number of features. Challenge 3: poorly scaled features. If features have very different scales, the ridge model might be biased towards features with larger magnitudes. Sample use case that resulted in challenge 3: one feature ranges from 0 to 100. While another feature ranges from 0 to 0.1. Fixes to challenge 3: scale the features to have similar ranges before training the ridge model. Common scaling techniques include standardization, zero mean, unit variance or min-max scaling values between 0 and 1. sklearn, Linear Model, SGD Classifier. Description: the SGD classifier in scikit-learn is a linear model that implements stochastic gradient descent (SGD) for classification. It is a versatile and efficient algorithm well suited for large datasets with high dimensionality. Inputs: X. This is the input feature matrix, where each row represents a sample and each column represents a feature. It should be a 2D array or a sparse matrix. Y. This is the target vector, representing the class labels for each sample in X. It should be a 1D array. Outputs: model. This is the trained SGD classifier model. You can use this model to make predictions on new data points. Predicted labels. This is the output of the predict method, which provides the class labels predicted by the trained model on new data. Steps: initialization. The algorithm starts by initializing the model's parameters, weights and biases randomly. Iteration: the algorithm iterates through the training data, taking one sample or a small batch of samples at a time. Gradient calculation for each sample. The algorithm calculates the gradient of the loss function with respect to the model's parameters. Parameter update. The parameters are updated by taking a step in the direction of the negative gradient. The step size is controlled by the learning rate. Repeat steps 2 to 4 are repeated for a specified number of epochs passes through the training data. Metrics: accuracy, the proportion of correctly classified samples in the test set. Precision, the proportion of correctly classified positive samples among all samples predicted as positive. Recall, the proportion of correctly classified positive samples among all actual positive samples. F1 score, the harmonic mean of precision and recall. Visualization plots. Decision boundary. This plot visualizes the decision boundary learned by the model. It is particularly useful for binary classification problems where the data can be visualized in 2D. Feature importance. This plot shows the importance of each feature in the classification decision, measured by the absolute value of the corresponding weight in the model. Fine-tune parameters. Loss, the loss function used to optimize the model. Common options include hinge for linear SVM, log for logistic regression, and modified Huber for robust regression. Penalty, the regularization term added to the loss function to prevent overfitting. Options include L2 for L2 regularization ridge regression and L1 for L1 regularization lasso regression. Alpha, the strength of the regularization term. Higher values correspond to stronger regularization. Learning rate, the step size taken during parameter updates. Options include constant, optimal, InvScaling, and adaptive. Eta 0 the initial learning rate used when learning rate is set to constant. Uncertainty methods. Confidence scores for probabilistic classifiers such as those with log loss. The model can output confidence scores representing the probability of each sample belonging to each class. These scores can be used to assess uncertainty. Challenges and fixes. Challenge 1 overfitting. This occurs when the model learns the training data too well, resulting in poor performance on unseen data. Sample use case. A model trained on a small dataset might overfit and struggle to generalize to new samples. Fixes to challenge 1. Increase the size of the training dataset. Add regularization L1 or L2 to the model. Adjust the hyperparameters, such as alpha, learning rate, and eta 0, to find a balance between bias and variance. Challenge 2 data scaling. The performance of SGD can be sensitive to the scale of features. Features with larger magnitudes can dominate the optimization process, leading to biased gradients and slow convergence. Sample use case. A dataset with features having widely different scales might lead to slow convergence and poor performance. Fixes to challenge 2. Use feature scaling techniques, such as standardization or normalization, to ensure all features have similar scales. Challenge 3. Choice of loss function. The choice of loss function can significantly impact model performance. For example, using a hinge loss for a dataset with outliers might lead to poor performance. Sample use case. Training a model with hinge loss on a dataset with outliers might result in a model that is highly sensitive to those outliers. Fixes to challenge 3. Use more robust loss functions, such as modified Huber, if the dataset contains outliers. sklearn, linear model, SGD1 class SVM. Description. This class implements a one-class SVM using a stochastic gradient descent SGD method. It can be used to detect novelties or outliers in data. The model learns a boundary that encapsulates the normal data points, and any data point outside this boundary is considered an outlier. Inputs. X a NumPy array of shape n samples. N features representing the training data. Y not applicable as this is an unsupervised learning method. Outputs. Self the fitted SGD1 class SVM object. Decision function X a NumPy array of shape n samples, containing the decision function values for the given data points. The decision function gives a score for each data point, where a positive score indicates that the point is likely to be an outlier. Steps. Initialization. Initialize the model with the specified parameters. Training. Use SGD to train the model on the given training data. The model learns the hyperplane that separates the normal data from the outliers. Prediction. Use the fitted model to predict the decision function values for new data points. Metrics. Accuracy. The percentage of correctly classified data points normal vs. outlier. Precision. The ratio of correctly classified outliers to the total number of predicted outliers. Recall. The ratio of correctly classified outliers to the total number of actual outliers. F1 score. The harmonic mean of precision and recall. Visualization plots. Scatter plot. Plot the data points in a 2D space, color coding them based on their decision function values. This can be useful for visualizing the learned decision boundary and identifying outliers. Fine-tune parameters. Penalty. The type of penalty to use for the loss function. Possible values are L2 penalty and L1 penalty. Alpha. The regularization parameter. Fit intercept, whether to fit an intercept term. Maxiter, the maximum number of iterations to run the SGD algorithm. Toll, the tolerance for the stopping criterion. Shuffle, whether to shuffle the training data before each epoch. Random state, the seed for the random number generator. Uncertainty methods. Confidence interval, calculate confidence intervals for the decision function values. This can be used to quantify the uncertainty in the model's predictions. Challenges and fixes. Challenge 1: overfitting to the training data. Sample use case that resulted in challenge 1: a dataset with a small number of outliers may lead to the model fitting the outliers too closely, resulting in poor performance on unseen data. Fixes to challenge 1. Increase the regularization parameter alpha. Use a smaller value for the penalty parameter. Reduce the number of iterations. Challenge 2: difficulty in handling high-dimensional data. Sample use case that resulted in challenge 2: in datasets with a large number of features. The model may struggle to learn a meaningful decision boundary. Fixes to challenge 2. Feature selection: select only the most relevant features for the task. Dimensionality reduction techniques: apply techniques like PCA or T-SNE to reduce the dimensionality of the data. Challenge 3: sensitivity to the choice of parameters. Sample use case that resulted in challenge 3: the performance of the model can be highly sensitive to the choice of parameters, such as penalty, alpha, and maxiter. Fixes to challenge 3. Use grid search or other hyperparameter optimization techniques to find the best set of parameters for the given data. Perform cross-validation to evaluate the model's performance on unseen data and ensure robustness. sklearn, linear model, linear regression. Description. Linear regression is a statistical method used to model the relationship between a dependent variable, the target, and one or more independent variables, the features. It aims to find the best fitting linear relationship, represented by a straight line or a hyperplane in higher dimensions, that minimizes the difference between the predicted and actual target values. Inputs. X, a 2D array-like structure representing the independent variable's features. Each row corresponds to a data point, and each column corresponds to a feature. Y, a 1D array-like structure representing the dependent variable target. It has the same number of elements as the rows in X, with each element corresponding to the target value for a specific data point. Outputs. Coa, a 1D array containing the coefficients of the linear model. Each element represents the coefficient for a corresponding feature in X. Intercept, a scalar value representing the intercept of the linear model. Steps. Model initialization: an instance of the linear regression class is created, potentially with specified parameters. Model training: the fit method is called with X and Y to train the model. It calculates the optimal coefficients score and intercept that minimize the difference between predicted and actual target values. Prediction: the predict method takes new data, new X values, and uses the learned coefficients and intercept to generate predictions for the target variable. Metrics. Mean squared error MSE measures the average squared difference between predicted and actual target values. Root mean squared error RMSE, the square root of MSE, providing a measure of the average error in the same units as the target variable. R squared represents the proportion of variance in the target variable that is explained by the linear model. A higher R squared value indicates a better fit. Visualization plots. Scatter plot with regression line visualizes the relationship between a specific feature and the target variable, with the fitted linear line overlaid. Residual plot shows the difference between predicted and actual target values, helping to assess the model's assumptions and identify potential issues. Fine-tune parameters. Fit-intercept Boolean indicating whether to calculate the intercept true or assume it is 0 false. Default is true. Normalize Boolean indicating whether to normalize the features true or not false. Default is false. Copix Boolean indicating whether to copy the input data true or modify it in place false. Default is true. Njobs integer specifying the number of jobs to run in parallel for faster computation. Default is none, meaning it uses all available cause. Uncertainty methods. Confidence intervals provide a range of plausible values for the target variable based on the model's uncertainty. Prediction intervals account for both model uncertainty and randomness in the data, providing a wider range than confidence intervals. Challenges and fixes. Challenge 1: multicollinearity when independent variables are highly correlated. It can lead to unstable coefficient estimates and make it difficult to interpret the model's results. Sample use case that resulted in challenge 1 using features like age and years of experience, which are likely to be highly correlated. Fixes to challenge 1. Feature selection: select only one of the highly correlated features or combine them into a single feature. Regularization techniques like ridge regression or lasso regression can penalize large coefficients, reducing the influence of multicollinearity. Challenge 2: outliers: extreme data points can significantly influence the fitted model, leading to inaccurate predictions and misleading interpretations. Sample use case that resulted in challenge 2: a data point with an unusually high target value or an outlier in a feature that strongly affects the target variable. Fixes to challenge 2. Outlier detection: identify and remove or transform outliers using methods like Z-score or IQR. Robust regression: use robust methods that are less sensitive to outliers, such as Theil-Sein regression or RANSAC. Challenge 3: nonlinear relationships: if the relationship between features and the target is not linear, linear regression may not be the best choice. Sample use case that resulted in challenge 3: a relationship between features and the target that resembles a curve or a more complex pattern. Fixes to challenge 3. Nonlinear transformation: apply transformations to the features, such as polynomial features or logarithmic transformations, to capture nonlinear relationships. Nonlinear models: consider using nonlinear models, such as decision trees, random forests, or support vector machines, which are better suited for capturing complex patterns. Challenge 4: insufficient data: having too little data can lead to overfitting, where the model learns the training data too well and performs poorly on unseen data. Sample use case that resulted in challenge 4: a limited number of data points available for training, particularly relative to the number of features. Fixes to challenge 4. Data augmentation: generate synthetic data points to increase the training dataset. Regularization: use regularization techniques to prevent overfitting by penalizing complex models. Feature selection: select the most relevant features to reduce the number of parameters the model needs to learn. Challenge 5: missing values. Missing values in the data can disrupt the model's training and lead to biased results. Sample use case that resulted in challenge 5: data points with missing values for certain features, potentially due to data entry errors or incomplete data collection. Fixes to challenge 5. Imputation: fill in missing values using techniques like mean imputation, median imputation, or more sophisticated methods like KNN imputation. Dropping rows or columns: remove rows or columns containing missing values if they represent a small proportion of the data. Feature engineering create new features that capture the information present in the missing values, such as indicator variables. sklearn, linear model, ridge. Description. Ridge regression is a linear regression model that adds a penalty term to the loss function. The penalty term is based on the sum of squared coefficients. This penalty term helps to prevent overfitting by shrinking the coefficients towards zero. Ridge regression is particularly useful when the number of features is large and the features are highly correlated. Inputs. X a 2D array of shape n samples. N features representing the input data. Each row represents a sample and each column represents a feature. Y a 1D array of shape n samples, representing the target values. Outputs. Core a 1D array of shape n features, representing the coefficients of the linear model. Intercept a scalar representing the intercept of the linear model. Steps. The model first calculates the loss function, which is the sum of squared errors between the predicted values and the actual values. The model then adds a penalty term to the loss function. The penalty term is based on the sum of squared coefficients. The model then uses an optimization algorithm to find the coefficients that minimize the loss function. Metrics. Mean squared error MSE, the average squared difference between the predicted values and the actual values. R squared, a statistical measure that represents the proportion of the variance in the dependent variable that is predictable from the independent variables. Visualization plots. Scatter plot of the predicted values vs the actual values. Residual plot of the errors vs the predicted values. Fine-tune parameters. Alpha, the regularization strength. A higher alpha value corresponds to a stronger penalty. Solver, the optimization algorithm used to fit the model. Fit intercept, whether to calculate the intercept of the linear model. Uncertainty methods. Confidence intervals, the range of values within which the true coefficient is likely to lie. Prediction intervals, the range of values within which the true target value is likely to lie. Challenges and fixes. Challenge 1, overfitting. Sample use case that resulted in challenge 1 when the number of features is large and the features are highly correlated. The model may overfit to the training data. Fixes to challenge 1 increase the value of alpha. This will shrink the coefficients towards zero and reduce overfitting. Challenge 2, underfitting. Sample use case that resulted in challenge 2 when the value of alpha is too high. The model may underfit to the training data. Fixes to challenge 2 decrease the value of alpha. This will allow the model to fit the training data more closely. sklearn, linear model, Ridge CV. Description. Ridge CV implements ridge regression with built-in cross-validation to select the best regularization parameter alpha. It aims to prevent overfitting by adding a penalty term to the loss function, which shrinks the coefficients towards zero. The optimal alpha value is chosen based on minimizing the cross-validation error, typically measured by mean squared error. Inputs. Alpha is a list or array of alpha values to be considered during cross-validation. Each alpha value represents the strength of the regularization penalty. Fit intercept, a boolean indicating whether to calculate the intercept term in the linear model. Normalize, a boolean indicating whether to normalize the features before fitting the model. CV, an integer or a cross-validation generator object determining the number of folds for cross-validation. Scoring, a string or callable object specifying the scoring metric to use during cross-validation. GCV mode, a string indicating the type of generalized cross-validation GCV to use, if applicable. Store CV values, a boolean indicating whether to store the cross-validation values for each alpha. Outputs. Coa, the coefficients of the fitted linear model. Intercept, the intercept term of the fitted linear model. Alpha, the optimal alpha value selected by cross-validation. CV values, if store CV values is true in array containing the cross-validation scores for each alpha value. Steps. Cross-validation, the input data is split into multiple folds. For each alpha value in the alphas list, the model is trained on all folds except one, and the error is calculated on the held out fold. Error calculation, the mean squared error or other specified scoring metric is calculated for each alpha value on the held out folds. Optimal alpha selection, the alpha value that minimizes the average cross-validation error is chosen as the optimal alpha. Model fitting, the ridge model is finally fitted using the optimal alpha value on the entire dataset. Metrics. Mean squared error MSE, the average squared difference between the predicted and actual values. R squared, the proportion of variance in the dependent variable explained by the model. Mean absolute error MA, the average absolute difference between the predicted and actual values. Visualization plots. Alpha vs cross-validation score, a plot visualizing the cross-validation scores for each alpha value. This helps understand how the model performs with different regularization strengths. Residual plot, a plot showing the difference between the predicted and actual values. This can reveal potential issues like non-linearity or heteroscedasticity. Fine-tune parameters. Alphas fine-tune the range of alpha values to explore the regularization strength that leads to optimal performance. CV adjust the number of folds for cross-validation to balance the trade-off between computation time and model generalization. Uncertainty methods. Bootstrap resampling, resample the data with replacement and refit the ridge CV model multiple times to obtain a distribution of coefficients and predictions. Bayesian methods integrate over the uncertainty of the model parameters to obtain credible intervals for predictions. Challenges and fixes. Challenge 1, overfitting to the training data. This can happen if the regularization strength is too low or if the data is highly correlated. Sample use case that resulted in challenge 1, a model with a small number of features and a large number of samples might overfit the training data. Fixes to challenge 1, increase the value of alpha to increase the regularization strength. Consider adding more features to the model to reduce the risk of overfitting. Challenge 2, poor performance on unseen data. This can happen if the cross-validation folds are not representative of the overall data distribution. Sample use case that resulted in challenge 2, using k-fold cross-validation with a small number of folds might result in biased estimates of the model performance. Fixes to challenge 2, use a larger number of folds for cross-validation. Consider using stratified k-fold cross-validation to ensure that each fold has a similar distribution of the target variable. Challenge 3, computationally expensive cross-validation can be computationally expensive, especially for large datasets or a wide range of alpha values. Sample use case that resulted in challenge 3, training ridge CV on a dataset with millions of samples and a large number of alpha values can take a long time. Fixes to challenge 3, consider reducing the number of folds for cross-validation. Use a smaller range of alpha values or employ techniques like early stopping to reduce the computation time. sklearn, linear model, SGD regressor. Description. SGD regressor implements a linear model trained by minimizing a regularized empirical loss function using gradient descent. The regularizer is a penalty added to the loss function that shrinks model parameters towards a zero vector using either L2 or L1 norm. This helps to prevent overfitting and improve generalization performance. SGD regressor can efficiently learn from large datasets, especially when combined with appropriate learning rate scheduling. Inputs. X. This is the input feature matrix, typically a NumPy array or pandas data frame. Each row represents a data point, and each column represents a feature. Y. This is the target variable, which represents the values to be predicted by the model. It can be a NumPy array or pandas series. Outputs. Self. The fitted SGD regressor object, containing the learned model parameters, including weights and intercept. This object can be used to make predictions on new data. Core. The learned weights for each feature in the model. Intercept. The learned intercept term of the model. Steps. Initialization. The model starts with random initial weights and an intercept. Gradient descent. The model iteratively updates the weights and intercept using the gradient descent algorithm. In each iteration, the model calculates the gradient of the loss function with respect to the weights and intercept, and then updates them in the opposite direction of the gradient, multiplied by the learning rate. Regularization during the training process. The loss function is penalized based on the magnitude of the weights L1 or L2 regularization. This helps prevent overfitting and improves the model's ability to generalize to new data. Metrics. Mean squared error MSE, a common metric used to evaluate the performance of regression models. It measures the average squared difference between the predicted and actual values. R-squared R2, a statistical measure that represents the proportion of variance in the target variable that is explained by the model. Higher R2 values indicate a better fit. Visualization plots. Residual plot, a plot that shows the difference between the predicted and actual values against the predicted values. This plot can help identify patterns in the residuals and assess the model's assumptions. Feature importance plot, a plot that shows the importance of each feature in the model. This plot can help identify the most influential features and understand the model's behavior. Fine-tune parameters. Loss. The loss function to be minimized during training. Common options include squared loss, Huber, and epsilon insensitive. Penalty. The type of regularization to be used. L2 for L2 regularization and L1 for L1 regularization. Alpha. The regularization strength. A higher value indicates stronger regularization. Learning rate. The learning rate used in the gradient descent algorithm. A smaller learning rate generally leads to slower convergence but can help avoid getting stuck in local optima. Eta 0. The initial learning rate for the constant learning rate schedule. Powered. The exponent for the InviaScaling learning rate schedule. Shuffle. Whether to shuffle the training data before each epoch. Uncertainty methods. Confidence intervals. Confidence intervals can be computed for the model's predictions. This provides a range within which the true value is likely to lie. Bayesian inference. A Bayesian approach can be used to estimate the uncertainty in the model. Parameters and predictions. Challenges and fixes. Challenge 1. Slow convergence. Gradient descent can be slow to converge, especially on large datasets with complex relationships. Sample use case training an SGD regressor on a large dataset with a high number of features and a complex target variable. Fixes. Increase the maximum number of iterations maxiter. Use a more efficient learning rate schedule InviaScaling or optimal. Reduce the batch size. Consider using a different optimization algorithm, e.g. ADAM. Challenge 2. Overfitting. The model may overfit to the training data, resulting in poor performance on unseen data. Sample use case training an SGD regressor on a dataset with a high number of features and a small number of data points. Fixes. Increase the regularization strength alpha. Use a different regularization technique, e.g. L1 regularization. Use early stopping to prevent the model from overfitting. Consider using feature selection techniques to reduce the number of features. Challenge 3. Poor generalization. The model may not generalize well to unseen data, especially if the training data is not representative of the real world. Sample use case training an SGD regressor on a dataset with a specific distribution of data points that does not reflect the true distribution of real-world data. Fixes. Collect more representative training data. Use data augmentation techniques to create more diverse training data. Consider using a different model that is better suited for the specific problem. Challenge 4. Sensitivity to outliers. The model can be sensitive to outliers, which can significantly affect the model's performance. Sample use case training an SGD regressor on a dataset with a few outliers that have a significant impact on the target variable. Fixes. Remove outliers from the dataset. Use a more robust loss function, e.g. Huber loss. Consider using a different model that is more robust to outliers. sklearn, linear model, ElasticNet. Description. ElasticNet is a linear regression model that combines the L1 and L2 penalties to regularize the model coefficients. This means that it can both shrink the coefficients of less important features towards zero and set the coefficients of unimportant features exactly to zero. It is a good choice when you have a large number of features and want to select a subset of features that are most important for predicting the target variable. Inputs. X a 2D array of shape n samples. N features representing the independent features. Y a 1D array of shape n samples, representing the dependent target variable. Outputs. Core a 1D array of shape n features, representing the coefficients of the linear model. Intercept a float representing the intercept of the linear model. Steps. The ElasticNet model is trained using the training data X, Y. The model uses a combination of L1 and L2 penalties to regularize the model coefficients. The L1 penalty shrinks the coefficients towards zero, while the L2 penalty prevents the coefficients from becoming too large. The model then predicts the target variable for new data using the learned coefficients and intercept. Metrics. Mean squared error MSE measures the average squared difference between the predicted values and the actual values. Mean absolute error MA measures the average absolute difference between the predicted values and the actual values. R squared R2 represents the proportion of variance in the dependent variable that is explained by the independent variable. Root mean squared error RMSE the square root of the MSE. Visualization plots. Scatter plot of the predicted values versus the actual values to assess the model's accuracy. Residual plot to check for heteroscedasticity and other patterns in the residuals. Fine-tune parameters. Alpha the strength of the L1 penalty. Increasing alpha will lead to more features being set to zero. L1 ratio the ratio between the L1 and L2 penalties. A value of 0 corresponds to pure L2 regularization ridge, while a value of 1 corresponds to pure L1 regularization lasso. Fit intercept whether to fit the intercept of the linear model. Normalize whether to normalize the input features. Uncertainty methods. Bootstrap resampling to estimate the uncertainty in the model coefficients. Bayesian methods to obtain a posterior distribution over the model coefficients. Challenges and fixes. Challenge 1, overfitting to the training data. Sample use case that resulted in challenge 1, a high degree of correlation between features, or a small sample size relative to the number of features. Fixes to challenge 1. Increase the regularization parameter alpha. Increase the L1 ratio. Use cross-validation to select the optimal hyperparameters. Challenge 2, high computational complexity for large datasets. Sample use case that resulted in challenge 2, large number of features or a large number of samples. Fixes to challenge 2. Use a stochastic gradient descent (SGD) solver. Use a sparse matrix representation for the data. Consider using a different model that is more scalable, such as a decision tree or random forest. sklearn, linear model, ElasticNet-CV. Description: ElasticNet-CV implements ElasticNet regression with automatic optimal hyperparameter selection using cross-validation. It combines the strengths of both ridge and lasso regression by penalizing both the L1 and L2 norms of the coefficients. This allows it to achieve sparsity like lasso while still mitigating the instability issues that arise from high correlations between features. ElasticNet-CV searches for the best combination of L1 and L2 regularization strengths, L1 ratio and alpha across a predefined grid, using cross-validation to evaluate the model's performance. Inputs: XA2D array representing the training features. Each row represents a sample, and each column represents a feature. YA1D array containing the target values. Outputs: COA, the coefficients of the linear model. Intercept, the intercept of the linear model. Alpha, the optimal L1 regularization strength alpha selected by cross-validation. L1 ratio, the optimal L1 ratio selected by cross-validation. Steps: preprocessing data is typically preprocessed before fitting the model. This may include scaling, normalization, or feature engineering. Hyperparameter tuning: ElasticNet-CV searches through a grid of L1 ratio and alpha values to find the combination that minimizes the chosen metric, e.g., mean squared error on a held-out validation set. Model training: the ElasticNet model is fitted to the training data with the optimal hyperparameters determined through cross-validation. Metrics: mean squared error (MSE), a common metric used to assess the model's prediction accuracy. R-squared, a measure of the goodness of fit of the model, indicating how well the model explains the variance in the target variable. Visualization plots: feature importance plot, a plot showcasing the relative importance of each feature based on the magnitude of their corresponding coefficients. Residual plot, a plot of the difference between the predicted values and the actual values, allowing you to visualize the model's performance and potential heteroscedasticity. Fine-tune parameters: L1 ratio, the mixing parameter between L1 and L2 regularization. A value of 1 corresponds to lasso, while a value of 0 corresponds to ridge. Alpha, the regularization strength. Higher values induce more sparsity, more features set to 0. CV, the number of folds for cross-validation. Higher values lead to more robust hyperparameter selection but increase computation time. APES, the tolerance for the optimization algorithm. Uncertainty methods. Confidence intervals for the model's coefficients. Confidence intervals can be calculated using the bootstrap method. Prediction intervals can be obtained using methods like Bayesian regression, or by estimating the uncertainty in the predictions based on the data distribution and the models. Variance, challenges and fixes. Challenge 1: overfitting. If the regularization strength is too low, the model may overfit to the training data and perform poorly on unseen data. Sample use case: a model trained on a small dataset with a lot of features may overfit, leading to high variance and poor generalization. Fixes: increase the alpha parameter or use a larger dataset. Apply early stopping to prevent overfitting during training. Challenge: 2. Poor feature selection: if the L1 ratio is too low, the model may not effectively select the most relevant features, potentially leading to a less parsimonious and interpretable model. Sample use case: a model trained with a low L1 ratio may include features that contribute little to the prediction, making it harder to understand the model's behavior. Fixes: increase the L1 ratio to promote stronger feature selection. Experiment with different feature selection methods alongside ElasticNet-CV. Challenge: 3. Computational complexity: ElasticNet-CV can be computationally expensive, especially with large datasets or high values of CV. Sample use case: training ElasticNet-CV with a large number of folds and features on a dataset with millions of samples can take a significant amount of time. Fixes: consider using a smaller number of folds or reducing the number of features. Utilize parallel computing or distributed training frameworks to accelerate the process. Challenge: 4. Interpretability: understanding the impact of individual features can be challenging, especially when the model selects a large number of features. Sample use case: it might be difficult to interpret the model's predictions if a significant number of features are used, making it hard to pinpoint the key drivers. Fixes: utilize feature importance plots or permutation feature importance to analyze the contributions of individual features. Consider using a more interpretable model, like a decision tree, if interpretability is paramount. Challenge: 5. Dealing with multicollinearity: ElasticNet is known to be sensitive to multicollinearity, high correlations between features, which can lead to unstable coefficient estimates. Sample use case: a dataset with highly correlated features may result in coefficients that vary significantly with slight changes in the data. Fixes: regularization is the main technique for handling this, but consider addressing multicollinearity by removing highly correlated features or applying dimensionality reduction methods like PCA before fitting the model. sklearn linear model LaRS. Description: the least angle regression LaRS algorithm is a method for fitting linear models that is particularly efficient when the number of features is large. It works by iteratively adding features to the model in a way that minimizes the angle between the residual vector and the current set of features. This makes it a good choice for problems with a high degree of collinearity among the features. LaRS is also closely related to the lasso algorithm, and can be used to implement lasso by simply stopping the LaRS algorithm at a certain point. Inputs: X. This is the feature matrix. A 2D array with shape n samples. N features. Each row represents a data point, and each column represents a feature. Y. This is the target vector. A 1D array with shape n samples. Each element represents the target value for the corresponding data point in X. Outputs: Core. This is a 1D array of shape n features that contains the estimated coefficients for each feature in the model. Intercept. This is a scalar value representing the estimated intercept of the model. Steps: initialization. The algorithm starts by initializing the coefficient vector to 0 and the residual vector to y. Feature selection. The algorithm then selects the feature that is most correlated with the current residual vector. Coefficient update. The coefficient for the selected feature is then updated in a way that minimizes the angle between the residual vector and the current set of features. Residual update. The residual vector is updated based on the new coefficient value. Repeat steps 2 to 4 are repeated until either all features have been included in the model or a stopping criterion has been met. Metrics. R-squared. This metric measures the proportion of variance in the target variable that is explained by the model. Mean squared error MSE. This metric measures the average squared difference between the predicted and actual values. Visualization plots. Coefficient path plot. This plot shows how the estimated coefficients changes the algorithm. Progressors. Residual plot. This plot shows the residuals of the model against the predicted values. Fine-tune parameters. Alpha. This parameter controls the strength of the L1 penalty. A higher value of alpha will result in a sparser model, with more features having coefficients of 0. Fit intercept. This parameter controls whether or not the model should include an intercept term. Normalize. This parameter controls whether or not the data should be normalized before fitting the model. Uncertainty methods. Confidence intervals. Confidence intervals can be used to estimate the uncertainty in the estimated coefficients. Bootstrapping. Bootstrapping can be used to estimate the uncertainty in the estimated model. Parameters. Challenges and fixes. Challenge 1. Collinearity. When features are highly correlated, the LAS algorithm can become unstable and produce unreliable results. Sample use case that resulted in challenge 1. A dataset with multiple features that are highly correlated, such as height and weight. Fixes to challenge 1. Feature selection. Remove highly correlated features from the dataset. Regularization. Use regularization techniques like lasso or ridge regression to penalize large coefficients and reduce the influence of correlated features. Challenge 2. High dimensionality. When the number of features is very large compared to the number of data points, the LAS algorithm can become computationally expensive. Sample use case that resulted in challenge 2. A dataset with thousands of features but only a few hundred data points. Fixes to challenge 2. Feature selection. Select a subset of features that are most likely to be relevant to the target variable. Dimensionality reduction. Use dimensionality reduction techniques like principal component analysis (PCA) to reduce the number of features. sklearn, linear model, LAS-CV. Description. LAS-CV implements the least angle regression LAS algorithm for finding the lasso solution. This algorithm is similar to forward stepwise regression but with an important difference. It uses a pathwise solution, which means that it starts from the null model and adds variables one by one until it reaches the full model. This path is continuous and is built by tracing the entire path of coefficients along the path. LAS-CV is a variant of LAS that uses cross-validation to automatically choose the optimal regularization parameter alpha. Inputs. X. The training data, where each row corresponds to a sample and each column corresponds to a feature. Y. The target variable. Outputs. Core. The estimated coefficients for each feature. Intercept. The estimated intercept. CV. Alphas. The values of alpha used for cross-validation. CVMSE. Path. The mean squared error for each value of alpha on the cross-validation folds. Steps. Step 1. The algorithm starts from the null model, i.e., the model with no features. Step 2. It then adds the feature that is most correlated with the target variable to the model. Step 3. It continues to add features one by one, always choosing the feature that is most correlated with the residual, the difference between the predicted and actual values. Step 4. The algorithm stops when all features have been added or when the desired regularization parameter has been reached. Metrics. Mean squared error MSE. This metric measures the average squared difference between the predicted and actual values. Visualization plots. Coefficient path plot. This plot shows the path of coefficients as a function of alpha. MSE path plot. This plot shows the MSE as a function of alpha. Fine-tune parameters. N alpha is the number of alpha values to use for cross-validation. CV the number of folds to use for cross-validation. Uncertainty methods. Bootstrap. This method can be used to estimate the uncertainty in the estimated coefficients. Challenges and fixes. Challenge 1. Overfitting. The model may overfit to the training data if the regularization parameter is not chosen correctly. Sample use case that resulted in challenge 1. The model may predict the training data very well, but it may perform poorly on unseen data. Fixes to challenge 1. Use cross-validation to choose the optimal regularization parameter. Challenge 2. High dimensionality. If the number of features is much larger than the number of samples, the LAS algorithm may be slow to run. Sample use case that resulted in challenge 2. The algorithm may take a long time to run on datasets with millions of features. Fixes to challenge 2. Use a feature selection method to reduce the number of features before running LAS. sklearn linear model LaSSO. Description. Explain in detail LaSSO. Least absolute shrinkage and selection operator is a linear model that uses L1 regularization to perform feature selection and avoid overfitting. It adds a penalty to the sum of absolute values of the regression coefficients. This penalty encourages smaller coefficients and even forces some coefficients to be exactly zero, effectively removing the corresponding features from the model. LaSSO is particularly useful when dealing with high-dimensional data where many features might be irrelevant or redundant. Inputs. XA2D array containing the training data features. Each row represents an instance, and each column represents a feature. YA1D array containing the target variable values corresponding to the training instances in X. Outputs. Core A1D array representing the learned regression coefficients for each feature. Intercept. The intercept term of the linear model. Steps. Initialize the regression coefficients often to 0. Iterate over the training data, updating the coefficients using a gradient descent-based algorithm. During each iteration, the algorithm also calculates the L1 penalty term and adds it to the overall cost function. The algorithm continues to iterate until convergence, meaning that the changes in the coefficients are below a certain threshold. Metrics. Mean squared error MSE measures the average squared difference between the predicted and actual target values. R squared represents the proportion of variance in the target variable that is explained by the model. Mean absolute error MA measures the average absolute difference between the predicted and actual target values. Visualization plots. Coefficient plot. A bar plot showing the magnitude and sign of each feature's coefficient. This plot helps visualize the feature importance and identify features that have been effectively removed by the LaSSO model. Residual plot. A scatter plot of the residuals, the differences between predicted and actual target values against the predicted values. This plot helps assess the model's assumptions and identify any systematic deviations from linearity. Fine-tune parameters. Alpha regularization strength. A higher alpha value leads to stronger regularization, resulting in more coefficients being forced to 0. Fit intercept Boolean flag indicating whether to fit an intercept term to the model. Normalize Boolean flag indicating whether to normalize the input features. Uncertainty methods. Confidence intervals calculated for the regression coefficients to estimate the uncertainty in their values. Bootstrapping, a method for estimating the uncertainty in model predictions by repeatedly sampling the training data with replacement and fitting the model to each sample. Challenges and fixes. Challenge 1: choosing the optimal alpha value. Sample use case that resulted in challenge 1: setting alpha too low may not provide enough regularization, leading to overfitting. Setting alpha too high may remove too many features, resulting in an underfit model. Fixes to challenge 1: use cross-validation techniques, e.g., grid search CV, to systematically search for the best alpha value that balances bias and variance. Challenge 2: handling highly correlated features. Sample use case that resulted in challenge 2: when features are highly correlated, Lasso may arbitrarily select one feature from the correlated group while setting the others to 0. Fixes to challenge 2: consider using feature selection methods, e.g., PCA, before applying Lasso to reduce the dimensionality of the data and address collinearity issues. sklearn, Linear Model, Lasso CV. Description: Lasso CV implements Lasso with cross-validation to select the best alpha. It searches over a range of alpha values and uses cross-validation to evaluate the performance of the model for each alpha. The best alpha is the one that results in the best cross-validation score. Inputs: X, the training data. This should be a 2D array of shape n samples. N features. Y, the target values. This should be a 1D array of shape n samples. Outputs: Coa, the coefficients of the linear model. This is a 1D array of shape n features. Intercept, the intercept of the linear model. Alpha, the optimal alpha value selected by cross-validation. Steps: fit the model using the provided training data and target values. Perform cross-validation to evaluate the model's performance for different alpha values. Select the alpha value that results in the best cross-validation score. Fit the model again using the selected alpha value. Metrics: R², the coefficient of determination, which measures the proportion of variance in the target variable that is explained by the model. Mean absolute error may, the average absolute difference between the predicted and actual target values. Mean squared error MSE, the average squared difference between the predicted and actual target values. Visualization plots: alpha vs. cross-validation score plot, a plot showing the cross-validation score for each alpha value. This plot helps to identify the optimal alpha value. Feature importance plot, a plot showing the magnitude of the coefficients for each feature. This plot helps to identify the most important features in the model. Fine-tune parameters. Alpha, the regularization strength. A higher alpha value results in stronger regularization. CV, the number of folds to use in cross-validation. Maxiter, the maximum number of iterations to use in the optimization algorithm. Toll, the tolerance for the optimization algorithm. Uncertainty methods. Cross-validation, using cross-validation to estimate the uncertainty in the model's predictions. Bootstrapping, resampling the training data multiple times and fitting the model to each resampled dataset to estimate the uncertainty in the model's parameters. Challenges and fixes. Challenge 1: overfitting to the training data. Sample use case that resulted in challenge 1: when the alpha value is too low, the model may overfit to the training data and perform poorly on unseen data. Fixes to challenge 1: increase the alpha value to increase the regularization strength. Challenge 2: the model may not converge if the alpha value is too high. Sample use case that resulted in challenge 2 when the alpha value is too high. The optimization algorithm may not be able to find a solution that satisfies the tolerance criteria. Fixes to challenge 2 decrease the alpha value or increase the maximum number of iterations. sklearn, linear model, LaSSou-Lars. Description. The LaSSou-Lars model is a linear regression model that utilizes the least angle regression LaRS algorithm to solve the lasso problem. The algorithm is similar to forward stepwise regression but with an important difference: it finds a whole path of coefficients as the lasso penalty parameter changes. This is a useful approach as it is often preferred to estimate an entire path of coefficients instead of a single coefficient. This allows for better visualization and analysis of the model's behavior. Inputs: X a 2D array of independent variables. Each row represents an observation, and each column represents a feature. Y a 1D array of dependent variables. Outputs: Coa 1D array of coefficients of the linear model. Intercept: the intercept of the linear model. Steps: the LaRS algorithm starts by selecting the feature that is most correlated with the target variable. It then moves along a direction that is equiangular between the selected feature and the next most correlated feature. It continues to move along this direction until it hits the constraint imposed by the lasso penalty. It then selects the next most correlated feature and repeats the process. Metrics: R-squared, a measure of how well the model fits the data. Mean squared error, MSE, a measure of the average squared error between the model's predictions and the actual values. Mean absolute error, MA, a measure of the average absolute error between the model's predictions and the actual values. Visualization plots: coefficient path plot, a plot of the coefficients as a function of the lasso penalty. Residual plot, a plot of the residuals, the difference between the model's predictions and actual values against the predicted values. Fine-tune parameters: alpha, the lasso penalty parameter. A larger value of alpha will lead to more coefficients being set to 0. Fit intercept, whether to fit an intercept to the model. Normalize, whether to normalize the features. APES, the stopping criterion for the LaRS algorithm. Uncertainty methods: bootstrap, resampling the data with replacement and fitting the model to each resampled dataset. The distribution of the coefficients can then be used to estimate the uncertainty. Cross-validation, dividing the data into multiple folds and fitting the model to each fold. The performance of the model can then be averaged across the folds to estimate the uncertainty. Challenges and fixes. Challenge 1: the LaRS algorithm can be computationally expensive for large datasets. Sample use case that resulted in challenge 1: fitting a LaSSou-Lars model to a dataset with millions of rows and thousands of columns. Fixes to challenge 1: use a smaller subset of the data for training. Use a more efficient implementation of the LaRS algorithm. Use a different regularization method, such as ElasticNet. Challenge 2: the LaRS algorithm can be sensitive to the choice of the lasso penalty parameter. Sample use case that resulted in challenge 2: selecting a lasso penalty parameter that is too small can lead to overfitting. Selecting a lasso penalty parameter that is too large can lead to underfitting. Fixes to challenge 2: use cross-validation to select the optimal lasso penalty parameter. Use a grid search to find the best lasso penalty parameter. Use a Bayesian optimization algorithm to find the best lasso penalty parameter. sklearn, linear model, LaSSou-Lars CV. Description. Lasso LAS CV implements Lasso model with least angle regression LAS and cross-validation to find the optimal alpha. It explores a range of alpha values using cross-validation, selecting the alpha that minimizes a chosen metric, typically the mean squared error MSE. Inputs: X a 2D array-like structure containing the independent variables. Each row represents a data sample, and each column represents a feature. Y a 1D array-like structure containing the dependent variable. It should have the same number of rows as the input array X. Outputs: Coa a 1D array containing the estimated coefficients for each feature. Intercept: the intercept term of the fitted model. Alpha: the optimal alpha value chosen through cross-validation. Steps: 1. The algorithm iteratively adds features into the model, starting with the feature most correlated with the target variable. 2. In each iteration, it computes the direction of the feature coefficient change and moves along this direction until another feature becomes as correlated with the target as the current feature. 3. The process continues, adding more features and updating the coefficients until a predetermined stopping condition is met, e.g., reaching a maximum number of features or exceeding a specified threshold. 4. Cross-validation is performed with a specified number of folds to evaluate the performance of a model across different alpha values. 5. The alpha value that minimizes the chosen metric, e.g., MSE, is selected as the optimal alpha. Metrics: mean squared error MSE, commonly used to evaluate the performance of linear regression models. R-squared, a metric that measures the proportion of variance in the dependent variable explained by the independent variables. Visualization plots: coefficient path plot. This plot visualizes the evolution of the feature coefficients as the algorithm iteratively adds features. It helps understand the impact of each feature on the model. Alpha vs. MSE plot. This plot shows the MSE values for different alpha values obtained during cross-validation. It allows visualization of the optimal alpha selection process. Fine-tune parameters: CV integer or cross-validation generator object. Number of folds to use for cross-validation. Maxiter: maximum number of iterations for the LAS algorithm. Apes: tolerance for the stopping criterion. Normalize: whether to normalize the input features. Precompute: whether to precompute the gram matrix. Fit intercept: whether to fit the intercept term. Verbose: verbosity level. Uncertainty methods. Confidence intervals. Confidence intervals can be calculated for the coefficients to assess the uncertainty in the estimated values. Challenges and fixes. Challenge 1: overfitting to the training data when the regularization strength is too low. Sample use case that resulted in challenge 1: when the alpha value is very small. The model tends to fit the training data very closely, leading to overfitting. Fixes to challenge 1: increase the regularization strength alpha. Challenge 2: underfitting to the training data when the regularization strength is too high. Sample use case that resulted in challenge 2: when the alpha value is too large. The model might not be able to capture the underlying relationships between the features and the target variable, leading to underfitting. Fixes to challenge 2: decrease the regularization strength alpha. YAML. sklearn, linear model, Lasso LAS IC. Description: this class implements Lasso model with least angle regression LAS and an information criteria to estimate the regularization parameter. The method is based on the least angle regression LAS algorithm that finds the entire regularization path. It uses a criterion based on the information content of the model to select the best regularization parameter. Inputs. X a 2D array of shape n samples. N features representing the training data, where n samples is the number of samples and n features is the number of features. Y a 1D array of shape n samples, representing the target variable. Outputs. Core a 1D array of shape n features, representing the coefficients of the features in the fitted model. Intercept a float representing the intercept of the fitted model. Alpha a float representing the optimal regularization parameter selected by the information. Criterion. Steps. The model iteratively adds features to the model, starting with the feature most correlated with the target variable. At each iteration, the model finds the direction that minimizes the residual sum of squares. The model then moves along this direction until another feature becomes as correlated with the residual as the current feature. This process continues until all features are added to the model. The model then uses an information criterion to select the optimal regularization parameter. Metrics. AIC information criterion, a metric that balances the goodness of fit of the model with the complexity of the model. Big Bayesian information criterion, a metric that penalizes models with more parameters. Visualization plots. Regularization path. This plot shows the coefficients of the features as a function of the regularization parameter. Information criterion. This plot shows the value of the information criterion as a function of the regularization parameter. Fine-tune parameters. Criterion. The information criterion to use for selecting the regularization parameter. Options include AIC information criterion or Big Bayesian information criterion. APES. The tolerance for the stopping condition. Uncertainty methods. Confidence intervals. The model can provide confidence intervals for the coefficients. Challenges and fixes. Challenge 1. High dimensionality of the feature space. Sample use case that resulted in challenge 1. When the number of features is very large, the model might take a long time to fit. Fixes to challenge 1. Consider using feature selection methods to reduce the dimensionality of the feature space before fitting the model. Challenge 2. Multicollinearity. Sample use case that resulted in challenge 2. When features are highly correlated, the model may be unstable and the coefficients may be sensitive to small changes in the data. Fixes to challenge 2. Consider using regularization techniques, such as lasso or ridge, to address multicollinearity. sklearn, linear model, orthogonal matching pursuit. Description. Orthogonal matching pursuit (OMP) is a greedy algorithm for sparse signal recovery. It aims to find the sparsest solution to a linear system of equations, assuming that the solution is sparse, meaning it has only a few non-zero elements. Inputs. X. The design matrix of shape n samples. N features, containing the features of the data. Y. The target vector of shape n samples, containing the target values. Outputs. Core. The estimated coefficients of the sparse solution. Intercept. The estimated intercept. Nit is the number of iterations run. Steps. Initialize the solution with zeros. Iteratively find the feature with the highest correlation with the current residual, the difference between the target and the current prediction. Add this feature to the active set. Update the coefficients using the least squares fit on the active set. Update the residual. Metrics. Mean squared error MSE measures the average squared difference between the predicted and actual target values. R squared represents the proportion of the variance in the target that is explained by the model. Sparsity measures the number of non-zero coefficients in the solution. Visualization plots. Feature importance plot visualizes the magnitude of the estimated coefficients, revealing the most influential features. Residual plot plots the difference between the predicted and actual target values, allowing assessment of model fit. Sparse solution visualization displays the non-zero coefficients of the solution, highlighting the sparse nature of the model. Fine-tune parameters. N non-zero coefs, the maximum number of non-zero coefficients to consider in the solution. Controls sparsity. Toll the tolerance for the stopping condition of the algorithm. Fit intercept, whether to estimate the intercept of the model. Uncertainty methods. Bootstrap resampling, repeatedly resampling the data and fitting the model to estimate the variability of the estimated coefficients. Bayesian linear regression provides a probabilistic framework to model uncertainty in the coefficients. Challenges and fixes. Challenge 1: overfitting. If the model is too sparse, it might overfit the training data and perform poorly on unseen data. Sample use case. A model with very few non-zero coefficients may perfectly fit the training data, but fail to generalize to new data. Fixes. Increase N non-zero coefs, allow the model to use more features, reducing the risk of overfitting. Regularization. Employ techniques like L1 or L2 regularization to penalize complex models and encourage more robust solutions. Cross-validation. Evaluate model performance on unseen data to detect overfitting and choose the best model hyperparameters. Challenge 2: choosing the optimal sparsity. Determining the appropriate level of sparsity can be challenging. Sample use case. Setting N non-zero coefs too low may miss important features, while setting it too high might include irrelevant features. Fixes. Experiment with different values of N non-zero coefs. Explore the effect of varying sparsity on model performance. Use cross-validation to find the optimal sparsity. Evaluate models with different levels of sparsity on unseen data and select the best. Employ model selection techniques. Use techniques like AIC or BIC to compare models with different sparsity levels and select the best one based on model complexity and data fit. sklearn, linear model, orthogonal matching pursuit CV. Description. Orthogonal matching pursuit CV implements orthogonal matching pursuit OMP with cross-validation to determine the optimal number of non-zero coefficients N non-zero coefs for sparse signal recovery. It searches for the sparsest solution that fits the data by iteratively adding features with the highest correlation to the residual inputs. X feature matrix of shape N samples. N features. Y target vector of shape N samples. Outputs. Core the estimated coefficients for the linear model. Intercept independent term in the linear model. N non-zero coefs, optimal number of non-zero coefficients determined through cross-validation. Steps. 1. Split the data into training and validation sets. 2. For each fold in cross-validation. A. Train an orthogonal matching pursuit model with a specified number of non-zero coefficients. B. Calculate the performance metric, e.g., mean squared error on the validation set. 3. Choose the number of non-zero coefficients that yields the best performance across the cross-validation folds. 4. Train the final orthogonal matching pursuit model with the selected N non-zero coefs on the entire training set. Metrics. Mean squared error MSE measures the average squared difference between predicted and actual values. R squared represents the proportion of variance in the target variable explained by the model. Visualization plots. Coefficient plot displays the estimated coefficients of the model, highlighting the selected non-zero coefficients. Fine-tune parameters. N non-zero coefs, number of non-zero coefficients to be selected in the model. This can be a range of values for cross-validation, or a single value if it's already known. CV the number of folds for cross-validation. Uncertainty methods. Bootstrapping, resampling the data with replacement and fitting the model multiple times to estimate the uncertainty in the coefficients. Challenges and fixes. Challenge 1. Overfitting when the model is too complex and captures noise in the data, leading to poor generalization. Sample use case that resulted in challenge 1 using a high number of non-zero coefficients or a small dataset. Fixes to challenge 1. Increase the size of the training data. Reduce the number of non-zero coefficients. Use regularization techniques like L1 or L2 penalties. Challenge 2. Feature selection bias when the feature selection process is biased towards certain features, leading to inaccurate model predictions. Sample use case that resulted in challenge 2 using a biased feature selection method or having correlated features in the data. Fixes to challenge 2. Use a more robust feature selection method. Remove correlated features from the data. Use feature scaling techniques to normalize feature values. sklearn, linear model, ARD regression. Description. ARD regression implements a Bayesian linear regression with automatic relevance determination ARD. It is designed to handle high-dimensional data and automatically identify irrelevant features. ARD assumes a prior distribution over the weights of the linear model, encouraging small weights for irrelevant features and effectively shrinking them towards zero. This leads to a sparse model, effectively performing feature selection. Inputs. X. The input features independent variables of the data as a 2D array of shape n samples. N features. Y. The target variable dependent variable as a 1D array of shape n samples. Outputs. Coa. The estimated coefficients of the linear regression model. It is a 1D array of shape n features. Intercept. The estimated intercept of the linear regression model. It is a scalar value. Steps. Initialization. The model initializes the prior distribution over the weights. The prior is assumed to be Gaussian with a zero mean and a variance specified by the alpha 1 parameter. Optimization. The model then uses an iterative optimization process, typically using the expectation maximization M algorithm, to find the posterior distribution over the weights. Prediction. Once the posterior distribution is found, the model can predict new target values based on new input features. Metrics. Mean squared error MSE. The average squared difference between the predicted and actual values. R squared. The proportion of the variance in the target variable that is explained by the model. Log likelihood. The likelihood of the data given the estimated model parameters. Visualization plots. Feature importance plot visualizes the estimated weights of the model, highlighting the importance of different features. Residual plot plots the difference between the predicted and actual values to check for patterns or trends. Prior and posterior distribution plots visualizes the prior and posterior distributions over the weights, showcasing the impact of the data on the model. Fine-tune parameters. Alpha 1. The prior variance of the weights. A higher value indicates a stronger prior belief in small weights. Alpha 2. The prior variance of the noise term. A higher value indicates a higher belief in noisy data. Niter. The maximum number of iterations in the optimization process. Tol. The convergence tolerance for the optimization process. Uncertainty methods. Bayesian inference. ARD regression is a Bayesian model, allowing for the estimation of the uncertainty associated with the predicted values. Credibility intervals. Bayesian methods can be used to calculate credibility intervals for predicted values, providing a range of plausible values. Challenges and fixes. Challenge 1. Slow training. The optimization process in ARD regression can be computationally expensive, especially for large datasets and high-dimensional feature spaces. Sample use case. Training a model on a dataset with millions of samples and thousands of features may take a significant amount of time. Fixes. Reduce the number of features. Feature selection techniques can be employed to reduce the dimensionality of the feature space. Optimize the hyperparameters. Experiment with different values for alpha 1, alpha 2, niter, and toll to improve training speed. Use a different optimization algorithm. Consider using alternative optimization algorithms like stochastic gradient descent or coordinate descent, which may be faster for large datasets. Challenge 2. Overfitting. ARD regression, like other Bayesian models, can overfit the data if the prior distribution is too weak or the training data is noisy. Sample use case. Training a model on a small dataset with high levels of noise may lead to overfitting, where the model learns the specific noise patterns rather than the underlying relationships in the data. Fixes. Increase the prior variance. Increase the alpha 1 and alpha 2 parameters to strengthen the prior belief in small weights and less noisy data. Regularization. Consider using additional regularization techniques, such as L1 or L2 regularization, to further constrain the model complexity. Cross-validation. Use cross-validation techniques to evaluate the model's performance on unseen data and identify potential overfitting. sklearn, linear model, Bayesian ridge. Description. The Bayesian ridge class implements a Bayesian approach to linear regression, utilizing a Gaussian prior over the model coefficients. This approach infers the posterior distribution of the coefficients, considering both the data and the prior assumptions. Unlike regular linear regression, Bayesian ridge provides probabilistic predictions and estimates the uncertainty associated with those predictions. It can handle high-dimensional datasets and is robust to overfitting. Inputs. X. A 2D array representing the features or independent variables of the dataset. Each row corresponds to a data point, and each column corresponds to a feature. Y. A 1D array representing the target variable or dependent variable. Outputs. Coa. A 1D array representing the estimated coefficients of the linear model. Each element corresponds to a feature. Intercept. The estimated intercept of the linear model. Steps. The model initializes the parameters with a Gaussian prior distribution. It iteratively updates the parameters based on the data and the prior assumptions. The model uses a conjugate prior distribution for the parameters, allowing for efficient computation of the posterior distribution. Metrics. R-squared, a measure of how well the model fits the data, ranging from 0 to 1, with higher values indicating a better fit. Mean squared error MSE, the average squared difference between the predicted values and the true values. Visualization plots. Scatter plot, a visual representation of the relationship between the predicted and actual values. Residual plot, a plot of the residuals differences between the predicted and actual values against the predicted values, which can help identify patterns or deviations from the model assumptions. Fine-tune parameters. Alpha, the regularization parameter for the prior distribution of the coefficients. A higher value corresponds to a stronger prior belief and reduces the model's complexity. Lambda, the regularization parameter for the prior distribution of the intercept. Uncertainty methods. Posterior distribution. The model provides the posterior distribution of the coefficients, allowing for the estimation of uncertainty in the predictions. Credible intervals. Confidence intervals based on the posterior distribution, indicating the range of values for the predictions with a certain probability. Challenges and fixes. Challenge 1. Overfitting to noisy data. If the data is noisy or contains outliers, the model might overfit and result in poor generalization performance. Sample use case that resulted in Challenge 1. A dataset with a high proportion of noisy data points can lead to overfitting. Fixes to Challenge 1. Increase the value of the alpha parameter to impose a stronger prior and reduce the model's complexity. Use techniques like data preprocessing to remove or mitigate outliers. Challenge 2. High dimensionality. When the number of features is large compared to the number of data points, the model might struggle to learn the relationships effectively. Sample use case that resulted in Challenge 2. A dataset with a large number of features but a limited number of data points can pose a challenge for the model. Fixes to Challenge 2. Use feature selection techniques to identify and remove irrelevant features. Consider alternative models like sparse Bayesian models that are more suitable for high-dimensional datasets. sklearn, linear model, multitask elastic net. Description: a linear model that minimizes a regularized loss function. It combines the L1 and L2 penalties in order to learn a sparse solution. This is useful when you have a large number of features and you want to find a model that is both accurate and interpretable. The elastic net penalty is a combination of the L1 and L2 penalties. The L1 penalty encourages sparsity by shrinking the coefficients of unimportant features to zero. The L2 penalty encourages robustness by shrinking the coefficients of highly correlated features toward each other. The multitask elastic net class is a specialized version of the elastic net class that is designed for multitask learning. Multitask learning is a technique where multiple related tasks are learned simultaneously. This can improve the performance of each individual task by sharing information across tasks. Inputs. X. The training data, where each row represents a sample and each column represents a feature. Y. The target values for the training data. Each row corresponds to a sample and each column represents a different task. Outputs. Core. The coefficients of the linear model. This is a 2D array where each row corresponds to a task and each column corresponds to a feature. Intercept. The intercept of the linear model. This is a 1D array where each element corresponds to a task. Steps. Initialize the model with the desired hyperparameters, such as the alpha and L1 ratio parameters. Fit the model to the training data using the fit method. Use the predict method to make predictions on new data. Metrics. Mean squared error (MSE), a common metric used to evaluate the performance of regression models. R-squared, a statistical measure of how well the regression model fits the data. Mean absolute error (MA), a measure of the average absolute difference between the predicted values and the actual values. Visualization plots. Scatter plot of the predicted values vs the actual values. This can be used to visually assess the accuracy of the model. Residual plot. This can be used to identify any patterns in the residuals that might indicate that the model is not a good fit for the data. Coefficient plot. This can be used to visualize the coefficients of the model and identify which features are most important. Fine-tune parameters. Alpha, the strength of the regularization. A higher value of alpha corresponds to stronger regularization. L1 ratio, the ratio of the L1 penalty to the L2 penalty. A higher value of L1 ratio corresponds to a stronger L1 penalty. Uncertainty methods. Confidence intervals can be used to estimate the uncertainty in the model's predictions. Bayesian inference can be used to quantify the uncertainty in the model's parameters. Challenges and fixes. Challenge 1: the model may be too complex and overfit the training data. Sample use case that resulted in Challenge 1: training a multitask elastic net model with a large number of features on a small dataset. Fixes to Challenge 1: use a smaller value of alpha to reduce the strength of the regularization. Increase the size of the training dataset. Challenge 2: the model may be too simple and not capture the underlying relationships in the data. Sample use case that resulted in Challenge 2: training a multitask elastic net model with a small value of alpha on a dataset with a high degree of nonlinearity. Fixes to Challenge 2: use a larger value of alpha to increase the strength of the regularization. Add more features to the model. Challenge 3: the model may not be able to handle data with a high degree of multicollinearity. Sample use case that resulted in Challenge 3: training a multitask elastic net model on a dataset where multiple features are highly correlated. Fixes to Challenge 3: use a smaller value of L1 ratio to reduce the strength of the L1 penalty. Perform feature selection to remove highly correlated features. Challenge 4: the model may be sensitive to the choice of hyperparameters. Sample use case that resulted in Challenge 4: trying to tune the alpha and L1 ratio parameters without using cross-validation. Fixes to Challenge 4: use cross-validation to find the optimal values for the hyperparameters. sklearn, linear model, multitask elastic net CV. Description: multitask elastic net CV is a linear model that fits multiple responses Y with an elastic net penalty. To minimize the sum of squared residuals, least squares, and the L1 and L2 norms of the coefficients. This is a multitask version of the elastic net. This implementation handles the case where the target is a 2D array of shape n samples. N targets. It will learn a separate coefficient vector for each target. The optimization objective for multitask elastic net CV is 12yx W2 alpha 1 L1 ratio W2 to L1 ratio W1, where point 1 is the L1 norm. Point 2 is the L2 norm. Alpha controls the overall strength of the penalty. L1 ratio controls the balance between the L1 and L2 penalties. The elastic net penalty mixes L1 and L2 regularization. It is useful for sparse models, similar to lasso, avoiding ill-conditioned models, similar to ridge regression. In order to select the optimal alpha and L1 ratio, a cross-validation scheme is used on the training set to find the values that minimize the mean squared error. Inputs: X array of shape n samples, n features. The training input samples. Y array of shape n samples, n targets. The target values. Outputs: core array of shape n targets, n features. The coefficients of the linear model. Intercept array of shape n targets. The independent term in the decision function. L1 ratio: the L1 ratio chosen by cross-validation. Alpha: the alpha chosen by cross-validation. Steps: fit the model to the data. Use cross-validation to find the optimal alpha and L1 ratio. Train the model with the optimal parameters. Metrics: mean squared error MSE, R squared, mean absolute error MA. Visualization plots: scatter plot of the target values vs the predicted values. Residual plot, coefficient plot. Fine-tune parameters. Alpha controls the overall strength of the penalty. L1 ratio controls the balance between the L1 and L2 penalties. N alpha's number of alpha values to test in cross-validation. NL1 ratio's number of L1 ratio values to test in cross-validation. CV cross-validation strategy. APE's tolerance for the optimization. Uncertainty methods. Confidence intervals to quantify the uncertainty in the coefficients. Prediction intervals to quantify the uncertainty in the predictions. Challenges and fixes. Challenge 1 multicollinearity. Sample use case that resulted in challenge 1 when the features are highly correlated. The model may be unstable and the coefficients may be difficult to interpret. Fixes to challenge 1. Remove highly correlated features. Use regularization methods, such as ridge regression or elastic net. Challenge 2 overfitting. Sample use case that resulted in challenge 2 when the model is too complex. It may overfit the training data and perform poorly on unseen data. Fixes to challenge 2. Use cross-validation to select the optimal model complexity. Use regularization methods, such as ridge regression or elastic net. Challenge 3 feature scaling. Sample use case that resulted in challenge 3 when the features are not scaled. The model may be biased towards features with larger scales. Fixes to challenge 3. Scale the features before training the model. Challenge 4 data imbalance. Sample use case that resulted in challenge 4 when the target values are imbalanced. The model may be biased towards the majority class. Fixes to challenge 4. Oversample the minority class. Undersample the majority class. Use weighted loss functions. Challenge 5 outliers. Sample use case that resulted in challenge 5 outliers in the data can significantly affect the model performance. Fixes to challenge 5. Remove outliers from the data. Use robust regression methods. Challenge 6 missing values. Sample use case that resulted in challenge 6 missing values in the data can cause problems for the model training. Fixes to challenge 6. Impute missing values. Use models that can handle missing values, such as decision trees or random forests. Challenge 7 categorical features. Sample use case that resulted in challenge 7 categorical features need to be encoded before training the model. Fixes to challenge 7. Use one-hot encoding. Use label encoding. sklearn, linear model, multitask lasso. Description. The multitask lasso class implements a multitask lasso regression model that learns a sparse set of coefficients for multiple related regression tasks. It leverages the lasso regularization technique to encourage sparsity, leading to feature selection across the tasks. Inputs. X-A2D array representing the training data. Each row represents a sample, and each column represents a feature. Y-A2D array representing the target values for each task. Each row represents a sample, and each column represents a task. Outputs. Core A2D array representing the learned coefficients for each feature and task. Intercept an array representing the intercepts for each task. Steps. The multitask lasso model iteratively minimizes a cost function that combines the squared error loss with a regularization term. The regularization term promotes sparsity in the coefficients, forcing coefficients for irrelevant features to be zero. Metrics. Mean squared error MSE measures the average squared difference between the predicted and actual target values. R squared indicates the proportion of variance in the target variable explained by the model. Visualization plots. Coefficient plot visualizes the learned coefficients for each feature and task. Scatter plot plots the predicted values against the actual target values for each task. Fine-tune parameters. Alpha regularization strength. Higher values lead to more sparsity. Fit intercept whether to fit an intercept for each task. Uncertainty methods. Bootstrap aggregation bagging trains multiple multitask lasso models on different subsets of data and averages the predictions to estimate uncertainty. Bayesian inference formulates the multitask lasso model as a Bayesian model and uses methods like Markov chain Monte Carlo MCMC to estimate the posterior distribution of the coefficients. Providing uncertainty estimates. Challenges and fixes. Challenge 1: overfitting when the number of features is high compared to the number of samples. Sample use case that resulted in challenge 1: a dataset with 1000 features and 100 samples, leading to overfitting and poor generalization. Fixes to challenge 1. Regularization: increase the alpha value to encourage more sparsity and prevent overfitting. Feature selection: select a smaller subset of features using methods like feature importance or L1. Regularization. Challenge 2: difficulty in interpreting the coefficients due to the shared sparsity pattern across tasks. Sample use case that resulted in challenge 2: a dataset with multiple tasks where the same features are important for different tasks, making it challenging to understand the specific contribution of each feature. Fixes to challenge 2. Feature grouping: group features based on their importance across tasks and analyze group-level coefficients. Task-specific analysis: explore the coefficients for each task individually to understand the unique contributions of features. sklearn, linear model, multitask lasso CV. Description. Multitask lasso CV is a linear model that learns a sparse solution for multiple response variables. It implements the multitask lasso with L1-L2 penalization, using cross-validation to choose the best regularization parameter. It is suitable for problems where the response variables are correlated and it is desirable to learn a shared set of features. Inputs. XA2D array representing the training data, where each row corresponds to an instance and each column corresponds to a feature. YA2D array representing the target values for each instance, where each column corresponds to a different response variable. Outputs. Core A2D array containing the coefficients of the learned model. The shape is n features, n tasks. Intercept A1D array containing the intercepts of the learned model. The shape is n tasks. Steps. The model uses cross-validation to find the best regularization parameter for the multitask lasso. For each fold in the cross-validation, the model fits the data using the current regularization parameter. The model then evaluates the performance on the holdout fold using a specified metric. The model selects the regularization parameter that yields the best performance across all folds. The model fits the entire training data using the selected regularization parameter to learn the final model coefficients. Metrics. R2 coefficient of determination, a measure of how well the model predicts the target values. Mean absolute error, a measure of the average absolute difference between the predicted and actual values. Visualization plots. Coefficient plots plot the coefficients of the learned model for each feature and task to visualize the sparsity pattern and the relationship between features and response variables. Prediction plots plot the predicted values against the actual values for each task to visually Assess the model's performance. Fine-tune parameters. Alpha is a list of regularization parameters to be considered by the cross-validation. CV the number of folds to use for cross-validation. Fit intercept whether to fit an intercept term. Uncertainty methods. Bootstrap resampling repeatedly draw samples with replacement from the original data and fit a model to each sample. The distribution of the model coefficients across the bootstrap samples can be used to estimate uncertainty. Bayesian methods incorporate prior information about the coefficients and use Bayesian inference to estimate their posterior distributions. The uncertainty is captured by the width of the posterior distributions. Challenges and fixes. Challenge 1. Overfitting the model might overfit the training data if the regularization parameter is too small. Sample use case. A model trained with a small regularization parameter might have high accuracy on the training data but perform poorly on unseen data. Fixes. Increase the regularization parameter to encourage sparsity and prevent overfitting. Use cross-validation to select the best regularization parameter. Challenge 2. High dimensionality. The model might struggle to learn accurate coefficients if the number of features is much larger than the number of samples. Sample use case. A model trained with a large number of features might have poor performance due to the curse of dimensionality. Fixes. Use feature selection techniques to reduce the number of features. Use dimensionality reduction techniques such as principal component analysis (PCA) to reduce the number of dimensions. Consider using a different model that is better suited for high-dimensional data, such as a random forest. Challenge 3. Multicollinearity. The model might have unstable coefficients if there is high correlation between features. Sample use case. A model trained with highly correlated features might have different coefficients for each fold of the cross-validation. Fixes. Use feature selection techniques to remove highly correlated features. Consider using a different model that is more robust to multicollinearity, such as ridge regression. Use regularization techniques, such as lasso or elastic net, to penalize large coefficients and reduce the influence of highly correlated features. sklearn, linear model, Huber regressor. Description. The Huber regressor is a robust linear regression model that combines the best of least squares regression and least absolute deviations regression. It is less sensitive to outliers in the data than least squares regression, while still providing a relatively smooth and continuous error function. Inputs. X the training data, which is a 2D array with each row representing a sample and each column representing a feature. Y the target values for the training data, which is a 1D array. Outputs. Coa the coefficients of the linear model, which are a 1D array. Intercept the intercept of the linear model. Steps. The Huber regressor uses a loss function that is quadratic for small errors and linear for large errors. This means that it penalizes large errors less than least squares regression, making it more robust to outliers. The model fits the data by minimizing the Huber loss function using an iterative algorithm. Metrics. Mean squared error MSE, the average squared difference between the predicted values and the true values. Mean absolute error MA, the average absolute difference between the predicted values and the true values. Visualization plots. Residual plot. This plot shows the difference between the predicted values and the true values. It can be used to identify outliers and assess the model's fit. Scatter plot of predicted values vs true values. This plot can be used to visually assess the model's performance. Fine-tune parameters. Epsilon. This parameter controls the size of the neighborhood around 0 where the loss function is quadratic. A smaller value of epsilon makes the model more robust to outliers. Alpha. This parameter controls the amount of regularization applied to the model. A larger value of alpha penalizes the model for having more complex coefficients. Uncertainty methods. Confidence intervals. These can be calculated using bootstrapping or other resampling methods to estimate the uncertainty in the model's predictions. Challenges and fixes. Challenge 1. The Huber regressor can be sensitive to the choice of the epsilon parameter. Sample use case that resulted in challenge 1. If epsilon is too small, the model may not be robust enough to outliers. If it is too large, the model may not be able to fit the data well. Fixes to challenge 1. The epsilon parameter can be tuned using cross-validation to find the optimal value. Challenge 2. The Huber regressor can be computationally expensive to fit, especially for large datasets. Sample use case that resulted in challenge 2. If the dataset is very large, it may take a long time to fit the model. Fixes to challenge 2. The Huber regressor can be used with stochastic gradient descent (SGD) to speed up the training process. sklearn, linear model, quantile regressor. Description. The quantile regressor is a linear model that predicts the quantiles of a target variable, allowing for the estimation of confidence intervals and uncertainty. It is based on the concept of quantile regression, where the goal is to minimize the sum of the weighted absolute errors between the predicted quantiles and the actual target values. Inputs. XA2D array representing the input features. YA1D array representing the target variable. Outputs. Predictions. A1D array containing the predicted quantiles for the given input features. Steps. The quantile regressor uses a linear model with a penalty term, e.g. L1 or L2 regularization to minimize the weighted absolute errors between the predicted quantiles and the actual target values. During training, the model learns the coefficients for the linear model, which represent the weights assigned to each input feature. For prediction, the model uses the learned coefficients and the input features to calculate the predicted quantiles. Metrics. Mean absolute error measures the average absolute difference between the predicted quantiles and the actual target values. Quantile loss. A specialized metric for quantile regression that measures the deviation from the target quantile. Visualization plots. Quantile QQ plot visualizes the distribution of the predicted quantiles against the actual target values to assess the model's performance in capturing the desired quantiles. Residual plot plots the difference between the predicted quantiles and the actual target values to identify any patterns or systematic errors. Fine-tune parameters. Alpha controls the strength of the regularization penalty. Higher values lead to stronger regularization, potentially reducing overfitting. Solver specifies the optimization algorithm used for training the model. Common options include LBFGS, LibLinear, and SAG. Quantile specifies the quantile to be predicted. For example, 0.5 corresponds to the median, 0.25 to the first quartile, and 0.75 to the third quartile. Uncertainty methods. Confidence intervals based on the predicted quantiles. The model can provide confidence intervals for the target variable, representing the range of plausible values. Challenges and fixes. Challenge 1. Overfitting to the training data. Sample use case that resulted in challenge 1 when the training data is small or noisy. The model may overfit, leading to poor generalization performance on unseen data. Fixes to challenge 1: increase the regularization strength higher alpha or use a different solver that is less prone to overfitting. Challenge 2: difficulty in capturing complex relationships between features and the target variable. Sample use case that resulted in challenge 2: if the relationship between the features and the target variable is highly nonlinear, a linear model may not be able to accurately capture it. Fixes to challenge 2: consider using a more flexible model such as a nonlinear model or adding more features that capture the nonlinear relationship. sklearn, linear model, RANSAC regressor. Description: RANSAC regressor implements the random sample consensus RANSAC algorithm, which is a robust method for fitting a linear model to data that contains outliers. RANSAC works by iteratively selecting a random subset of the data, the inliers, and fitting a linear model to this subset. Then, it measures the error between the fitted model and the rest of the data points. The data points with low errors are considered inliers, while those with high errors are considered outliers. This process is repeated multiple times, and the model with the highest number of inliers is chosen as the final model. Inputs: X, the training data, represented as a 2D array. Each row corresponds to a data point, and each column corresponds to a feature. Y, the target values for the training data, represented as a 1D array. Outputs: Coa, the coefficients of the fitted linear model. Intercept, the intercept of the fitted linear model. Steps: randomly selects a subset of the data, the inliers. Fits a linear model to the inliers. Calculates the error between the fitted model and the rest of the data points. Identifies the data points with low errors inliers and those with high errors outliers. Repeats steps 1 to 4 multiple times. Selects the model with the highest number of inliers as the final model. Metrics: R2 score, a measure of how well the fitted model explains the variation in the target values. Mean squared error MSE, a measure of the average squared error between the predicted values and the actual values. Visualization plots: scatter plot of the data with the fitted regression line. Residual plot, showing the difference between the predicted values and the actual values. Fine-tune parameters: min samples, the minimum number of data points required to fit a model. Residual threshold, the maximum error allowed for a data point to be considered an inlier. Max trials, the maximum number of iterations to perform. Random state, the seed for the random number generator. Uncertainty methods: bootstrap, resampling the data with replacement to estimate the uncertainty in the fitted. Coefficients and predictions: Bayesian inference, using a probabilistic model to estimate the uncertainty in the fitted. Coefficients and predictions. Challenges and fixes. Challenge 1: the RANSAC algorithm can be sensitive to the choice of the residual threshold parameter. If the threshold is too high, the algorithm may include outliers in the inlier set, leading to a poor fit. If the threshold is too low, the algorithm may exclude valid data points, leading to an incomplete fit. Sample use case that resulted in challenge 1: a dataset containing a large number of outliers with a high residual threshold. Fixes to challenge 1: use cross-validation to determine the optimal value for the residual threshold. Use a more robust method for fitting the linear model, such as the Theil-Sein estimator. Challenge 2: the RANSAC algorithm can be computationally expensive, especially for large datasets. Sample use case that resulted in Challenge 2: a dataset with millions of data points. Fixes to Challenge 2. Reduce the number of iterations by using a smaller value for the max trials parameter. Use a more efficient algorithm for fitting the linear model, such as the least squares estimator. Use a parallel processing framework to speed up the computation. sklearn, linear model, Thielsen regressor. Description: Thielsen regressor is a robust linear regression model that is resistant to outliers in the data. It estimates the regression coefficients using a robust estimator based on the Thielsen estimator, which is a non-parametric method that considers the slope of lines drawn between all pairs of data points. This makes it more reliable than ordinary least squares OLS regression when the data contains outliers or deviations from a linear relationship. Inputs: X a 2D array of independent variables, Y a 1D array of dependent variables. Outputs: Coa a 1D array representing the estimated regression coefficients. Intercept: the estimated intercept of the regression line. Steps: The algorithm computes the slope of the line passing through every pair of data points. The median of these slopes is selected as the robust estimate of the slope of the linear relationship. The intercept is calculated using the estimated slope and the median of the dependent variable. Metrics: Mean squared error MSE measures the average squared difference between the predicted and actual values. R squared represents the proportion of variance in the dependent variable explained by K. Independent variables. Visualization plots. Scatter plot with the regression line visualizes the relationship between the independent and dependent variables with the fitted line. Residual plot plots the difference between the predicted and actual values to check for patterns that indicate model misspecification. Fine-tune parameters. Fit intercept: a Boolean parameter that determines whether to include an intercept term in the model. Random state: an integer or none, used to control the random number generator for shuffling the data. Uncertainty methods. Confidence intervals quantify the uncertainty in the estimated coefficients and intercepts. Bootstrapping: a resampling technique that generates multiple regression models by randomly sampling with replacement from the data to estimate the uncertainty in the model parameters. Challenges and fixes. Challenge 1: high computational cost for large datasets. Calculating the slope of every pair of points can be computationally expensive for datasets with a large number of samples. Sample use case: a dataset with millions of data points. Fixes to Challenge 1. Use a subset of the data for model fitting. Subsampling the data can reduce the computational burden without significantly affecting the accuracy of the model. Use a faster algorithm. Some implementations of the Thielsen estimator use faster algorithms for calculating the slopes, such as the quick select algorithm. Challenge 2: sensitivity to the number of outliers. The Thielsen estimator can be sensitive to the number of outliers in the data, and the results can be skewed if the proportion of outliers is significant. Sample use case: a dataset with a high percentage of outliers. Fixes to Challenge 2. Pre-processing the data to remove outliers. Outliers can be identified using techniques like Z-score or IQR interquartile range and removed from the dataset before fitting the model. Use a different robust estimator for datasets with a high proportion of outliers. Consider using a different robust estimator, such as the RANSAC algorithm, which is more resistant to outliers. sklearn, linear model, Poisson regressor. Description: a Poisson regression model that uses a generalized linear model GLM with a Poisson distribution to predict count data. It assumes that the target variable follows a Poisson distribution, which means that it represents the number of events occurring in a fixed interval of time or space. The model estimates the parameters of the linear function that relates the features to the expected value of the target variable. Inputs: X, a 2D array-like object representing the features or independent variables. Each row represents a sample, and each column represents a feature. Y, a 1D array-like object representing the target variable or dependent variable. It should contain count data. Outputs: Coa, a 1D array representing the coefficients of the linear model. The coefficients correspond to the weights assigned to each feature. Intercept, a scalar value representing the intercept of the linear model. Steps: the model uses maximum likelihood estimation to find the optimal values of the coefficients in intercept that minimize the negative log likelihood function. The model predicts the expected value of the target variable for each sample based on the linear combination of its features and the learned coefficients and intercept. Metrics: mean absolute error measures the average absolute difference between the predicted and actual values. Root mean squared error RMSE measures the square root of the average squared difference between the predicted and actual values. Log loss measures the average negative log likelihood of the model. Visualization plots: residual plot displays the difference between the predicted and actual values to assess the model's fit and detect potential patterns or outliers. Scatter plot visualizes the relationship between the predicted and actual values. Fine-tune parameters: alpha regularization parameter that controls the strength of L2 regularization. Higher values promote sparsity and prevent overfitting. Fit intercept Boolean flag that indicates whether to estimate the intercept term in the linear model. Maxiter maximum number of iterations for the optimization algorithm. Solver algorithm used to solve the optimization problem. Common options include LBFGS, Newton CG, and SAG. Uncertainty methods. Confidence intervals provides a range of values around the predicted value, representing the uncertainty in the prediction. Prediction intervals provides a wider range of values, taking into account both the uncertainty in the model parameters and the inherent variability in the data. Challenges and fixes. Challenge 1: over dispersion. The observed variance of the target variable is greater than the expected variance under the Poisson distribution. Sample use case count data with a higher degree of variability than expected by the Poisson distribution. Fixes. Consider using a more flexible distribution, such as the negative binomial distribution. To model over-dispersion, use robust estimation techniques that are less sensitive to outliers. Include additional features in the model to explain the extra variability. Challenge 2: zero inflation. The number of zero values in the target variable is significantly higher than expected under the Poisson distribution. Sample use case count data where a large proportion of samples have zero counts. Fixes. Utilize a zero-inflated Poisson regression model, which accounts for the excess zeros in the data. Consider using a mixture model that combines a Poisson distribution for non-zero counts and a separate component for zero counts. Explore data transformations to address zero inflation. sklearn, linear model, 2D regressor. Description: a generalized linear model GLM with 2D distribution for the response variable. This model is particularly useful for modeling count data, where the response variable represents the number of events occurring within a given time interval or space. The Tweedy distribution encompasses a range of distributions, including Poisson, gamma, and compound Poisson distributions, allowing it to handle different types of count data with varying degrees of overdispersion. Inputs. X, a two-dimensional array representing the input features or independent variables. Each row corresponds to a sample, and each column represents a feature. Y, a one-dimensional array representing the target variable or dependent variable. This array contains the count data for each sample. Outputs. Coefficients, a one-dimensional array containing the estimated coefficients for each feature. The coefficients indicate the strength and direction of the relationship between each feature and the response variable. Intercept, a scalar value representing the intercept of the fitted model. The intercept represents the expected value of the response variable when all features are 0. Predictions, a one-dimensional array containing the predicted values for the response variable based on the fitted model. These predictions can be used for various purposes, such as forecasting or classification. Steps. Model initialization. Create an instance of the Tweedy regressor class, specifying the desired parameters. Model training. Fit the model to the input data X, Y using the fit method. This involves estimating the model coefficients and intercept that minimize the specified loss. Function. Prediction. Generate predictions for new input data using the predict method. This involves applying the estimated coefficients and intercept to the input features. Metrics. Mean absolute error may measures the average absolute difference between the predicted and actual values. Mean squared error MSE measures the average squared difference between the predicted and actual values. Root mean squared error RMSE measures the square root of the mean squared error. R squared R2 indicates the proportion of variance in the response variable that is explained by the model. Visualization plots. Residual plots plots the residuals differences between predicted and actual values against the predicted values. This helps identify patterns or trends in the residuals, suggesting potential problems with the model. Prediction vs. actual plots plots the predicted values against the actual values. This helps visualize the model's performance and identify potential biases or outliers. Fine-tune parameters. Power controls the shape of the Tweedy distribution. The default value is 1.0, representing the Poisson distribution. Other values can be used to model different types of count data. Alpha, the regularization strength. A higher value increases the regularization effect, which can help prevent overfitting. Fit intercept specifies whether to include an intercept term in the model. The default value is true. Solver specifies the optimization algorithm used to estimate the model parameters. Uncertainty methods. Confidence intervals provide a range of values around the predicted value that represents the uncertainty in the prediction. Prediction intervals provide a range of values that captures a certain level of confidence, e.g., 95 that the true value falls within. Challenges and fixes. Challenge 1. Overdispersion in count data. This occurs when the variance of the response variable is greater than the mean, violating the assumption of the Poisson distribution. Sample use case. Analyzing the number of accidents on a highway over a month, where the variance is significantly higher than the mean. Fixes. Use a Tweedy distribution with a power value greater than 1.0 to account for the overdispersion. Consider using a negative binomial regression model, which is specifically designed for overdispersed count data. Challenge 2. Zero inflation in count data. This occurs when there is a higher proportion of zeros in the data than expected under the Poisson distribution. Sample use case analyzing the number of purchases made by customers at a store, where a large number of customers made no purchases. Fixes. Use a zero-inflated Poisson ZIP or zero-inflated negative binomial ZINB regression model to account for the excess zeros. Separate the data into two groups, zero and non-zero, and fit separate models to each group. Challenge 3. Nonlinear relationship between features and response. The Tweedy regressor assumes a linear relationship between the features and the response. Sample use case modeling the number of website visits based on advertising spend, where the relationship may be nonlinear. Fixes. Transform the features using nonlinear functions, e.g., polynomial terms, logarithmic transformations to capture the nonlinear relationship. Use a nonlinear model, e.g., decision tree. Support vector machine that can handle nonlinear relationships. Challenge 4. Collinearity among features. High collinearity between features can lead to unstable coefficient estimates. Sample use case modeling the number of sales based on both price and discount, where price and discount are highly correlated. Fixes. Remove one of the correlated features. Use regularization techniques, e.g., L1 or L2 regularization to penalize large coefficients and reduce the impact of collinearity. sklearn, linear model, gamma regressor. Description. A gamma regressor model in scikit-learn is used to predict the target variable using a gamma distribution model, which is a continuous probability distribution that is frequently used to model positively skewed data. It is particularly suited for scenarios where the target variable is non-negative and exhibits a positive skew. Inputs. X. This is the input feature matrix. A 2D array where each row represents a data point, and each column represents a feature. Y. This is the target variable. A 1D array representing the values to be predicted. Outputs. Model the trained gamma regressor model. YPRED the predicted target values based on the trained model. Steps. Initialization. A gamma regressor object is created with desired parameters. Training. The model is trained by fitting it to the input features X and the target variable Y. Prediction. The trained model is used to predict the target values for new input features X. Metrics. Mean squared error. MSE measures the average squared difference between the predicted and actual target values. Root mean squared error. RMSE represents the square root of the MSE and provides a measure of P. Model's prediction error in the same units as the target variable. R squared indicates the proportion of the variance in the target variable that is explained by the model. Mean absolute error may calculates the average absolute difference between the predicted and actual target values. Visualization plots. Residual plot shows the difference between the predicted and actual values, helping to identify patterns in the model's errors. Scatter plot displays the relationship between the predicted and actual target values. Fine-tune parameters. Alpha regularization strength that helps prevent overfitting by penalizing large coefficients. Fit intercept determines whether to add an intercept term to the model. Uncertainty methods. Confidence intervals provide a range of values within which the true target value is likely to fall, based on the model's uncertainty. Challenges and fixes. Challenge 1. Overfitting. The model might overfit the training data, leading to poor performance on unseen data. Sample use case that resulted in challenge 1. When the training dataset is small and contains noise, the model might learn the noise instead of the underlying patterns. Fixes to challenge 1. Increase the regularization strength alpha to penalize complex models and encourage simpler ones. Use cross-validation to evaluate the model's performance on unseen data and identify potential overfitting. Challenge 2. Data skewness. The gamma distribution is typically used for positively skewed data. If the data is not skewed or has a different skewness, the model may not perform well. Sample use case that resulted in challenge 2. If the target variable is evenly distributed or negatively skewed, the gamma distribution might not be an appropriate model. Fixes to challenge 2. Consider alternative regression models that are better suited for the specific data distribution. Apply data transformations to make the data more suitable for the gamma distribution. Use a different regression model that is better suited for the specific data distribution, such as a linear regression or a generalized linear model (GLM). sklearn, linear model, passive-aggressive regressor. Description: the passive-aggressive regressor is a linear model that is trained using the passive-aggressive algorithm. This algorithm is a type of online learning algorithm that updates its model parameters based on the errors it makes on individual training examples. Inputs: X, the training data, where each row represents a data point and each column represents a feature. Y, the target values for the training data. Outputs: Self, the trained passive-aggressive regressor object. Core, the coefficients of the linear model. Intercept, the intercept of the linear model. Steps: the passive-aggressive regressor initializes its model parameters with random values. For each training example, the model makes a prediction. If the model makes an error, the model updates its parameters in a way that minimizes the error. The update rule for the parameters is based on the error and the learning rate. The learning rate controls how much the model's parameters are updated based on each error. Metrics: mean squared error (MSE), the average squared difference between the predicted values and the actual values. Mean absolute error (MAE), the average absolute difference between the predicted values and actual values. R-squared, a measure of how well the model fits the data. Visualization plots: scatter plot of the predicted values versus the actual values. Residual plot, a plot of the difference between the predicted values and the actual values versus the predicted values. Fine-tune parameters: see the penalty parameter that controls the strength of the regularization. A higher value of C means that the model is more likely to overfit to the training data. A lower value of C means that the model is more likely to underfit to the training data. Fit intercept: whether to fit an intercept term to the model. If set to true, the model will include an intercept term in the linear model. If set to false, the model will not include an intercept term in the linear model. Maxiter: the maximum number of iterations to run the training algorithm. A higher value of maxiter means that the model will be trained for longer, which may lead to better performance. A lower value of maxiter means that the model will be trained for shorter, which may lead to worse performance. Toll: the tolerance for the stopping criterion. A lower value of toll means that the model will be trained for longer, which may lead to better performance. A higher value of toll means that the model will be trained for shorter, which may lead to worse performance. Random state: the random seed to use for the training algorithm. This parameter is useful for ensuring that the model is trained with the same random numbers each time. Uncertainty methods. Confidence intervals, the range of values that the model predicts with a certain level of confidence. Prediction intervals, the range of values that the model predicts with a certain level of confidence, taking into account the uncertainty in the model's parameters. Challenges and fixes. Challenge 1. Overfitting. The model may overfit to the training data, which means that it performs well on the training data but poorly on unseen data. Sample use case that resulted in challenge 1. The model is trained on a small dataset, which can lead to overfitting. Fixes to challenge 1. Regularization. Use regularization techniques such as L1 or L2 regularization to prevent the model from overfitting. Cross-validation. Use cross-validation to evaluate the model's performance on unseen data. Challenge 2. Underfitting. The model may underfit to the training data, which means that it does not perform well on the training data or on unseen data. Sample use case that resulted in challenge 2. The model is trained on a dataset with a lot of noise, which can lead to underfitting. Fixes to challenge 2. Feature engineering. Add new features to the model that are more informative. Increase the number of training examples. Use a larger dataset to train the model. Increase the complexity of the model. Use a more complex model such as a neural network. YAML. sklearn. Linear model. NetPath. Description. The NetPath function in scikit-learn's linear model module implements the elastic net regularization path. It calculates a sequence of models, each with a different value of the regularization parameter L1 ratio, while keeping the other parameters constant. This allows exploring the trade-off between model complexity measured by the number of non-zero coefficients and prediction accuracy. Inputs. X a 2D array of shape n samples. N features representing the training data features. Y a 1D array of shape n samples, representing the target values. L1 ratio of float between 0 and 1 representing the mixing parameter. A value of 0 corresponds to ridge regression L2 penalty and a value of 1 corresponds to lasso regression L1 penalty. Apes a float representing the tolerance for the stopping criterion defaults to 1e-3. N alphas an integer representing the number of alphas to compute defaults to 100. Alphas an array of floats representing the values of the regularization parameter alpha to compute. Fit intercept a boolean indicating whether to fit an intercept term defaults to true. Normalize a boolean indicating whether to normalize the data defaults to false. Precompute a string or array like indicating whether to precompute the gram matrix defaults to false. Copix a boolean indicating whether to copy the input data defaults to true. Verbose an integer representing the verbosity level defaults to 0. Outputs. Alphas a 1D array of shape n alphas, representing the values of the regularization parameter alpha for which the models were computed. Coefficients a 2D array of shape n alphas. N features representing the coefficients of the models for each alpha. Knitters a 1D array of shape n alphas, representing the number of iterations required to compute each model. Steps. The NetPath function calculates a sequence of elastic net models, each with a different value of the regularization parameter L1 ratio. For each value of L1 ratio, the function uses a coordinate descent algorithm to solve the optimization problem for different values of alpha. The resulting models are stored in the coefficients output, along with the corresponding alpha values. Metrics. R-squared, a measure of the proportion of variance in the target variable that is explained by the model. Mean absolute error may a measure of the average absolute difference between the predicted and actual values. Mean squared error MSE a measure of the average squared difference between the predicted and actual values. Visualization plots. Coefficient path plot, a plot of the coefficients for each feature across different values of alpha. This allows visualizing the sparsity pattern of the models and the impact of regularization on feature selection. Regularization path plot, a plot of the regularization parameter alpha against the corresponding R-squared, MA, or MSE values. This allows visualizing the trade-off between model complexity and prediction accuracy. Fine-tune parameters. L1 ratio controls the balance between the L1 and L2 penalties. A higher L1 ratio emphasizes sparsity, while a lower value emphasizes the ridge penalty. Alpha, the regularization parameter, controls the strength of the penalty. A higher alpha value leads to more regularization and sparser models. Apes, the tolerance for the stopping criterion. A lower value results in more accurate solutions but can be computationally expensive. Uncertainty methods. Confidence intervals. Confidence intervals for the coefficients can be calculated using methods like bootstrapping or cross-validation. Bayesian inference. A Bayesian approach can be employed to incorporate prior information about the coefficients and estimate their posterior distributions, which can be used to quantify uncertainty. Challenges and fixes. Challenge 1. Overfitting. When the model is too complex, it may overfit the training data, leading to poor performance on unseen data. Sample use case that resulted in Challenge 1. A high-dimensional dataset with a large number of features and a small number of samples. Fixes to Challenge 1. Increase the value of alpha to introduce more regularization. Use cross-validation to evaluate model performance and select the optimal value of alpha. Consider using feature selection techniques to reduce the number of features. Challenge 2. Computational complexity. Computing the regularization path can be computationally expensive for large datasets or a large number of alphas. Sample use case that resulted in Challenge 2. A very large dataset with millions of samples and features. Fixes to Challenge 2. Reduce the number of alphas to compute. Use a more efficient algorithm like stochastic coordinate descent. Consider using parallel computing to speed up computation. sklearn, linear model, Laws path. Description. The least angle regression Laws algorithm finds the solution path for a linear model by progressively adding variables into the model in a greedy fashion. It provides a more efficient way to compute the entire regularization path compared to using the coordinate descent algorithm as in Lasso for a large number of features. Inputs. X. This is the input feature matrix. It should be a 2D array of shape n samples. N features. Y. This is the target variable. A 1D array of shape n samples. Outputs. Copath. A 2D array of shape n features. N steps containing the coefficients of each feature at each step of the Laws path. Intercept path. A 1D array of shape n steps, containing the intercept of the model at each step. Active. A list of lists, where each inner list contains the indices of the active features at each step. Steps. Initialization. Start with an empty model, no features included, and a residual equal to the target variable. Feature selection. Find the feature with the highest correlation with the current residual. This is the feature that would contribute the most to reducing the residual. Step direction. Determine the direction in which to move the coefficient of the selected feature. The direction is either towards its positive or negative correlation with the residual. Step size. Calculate the step size for moving the coefficient along the direction. The step size is chosen so that the coefficient of the selected feature reaches a point where another feature has the same correlation with the residual. Update model. Update the model by adding the selected feature and its corresponding coefficient. Update the residual accordingly. Repeat steps. Continue steps 2 to 5 until all features have been added to the model or the desired number of steps have been reached. Metrics. R² measures the proportion of variance in the dependent variable explained by the independent variables in the model. Mean squared error. MSE measures the average squared difference between the predicted and actual values. Visualization plots. Coefficient path plots the coefficient values of all features against the last path steps. This visualization shows how the importance of each feature changes as the model progresses. Residual plot plots the residual values against the fitted values. This can help identify patterns in the data and check for heteroscedasticity. Fine-tune parameters. APES. This parameter controls the tolerance for the convergence of the algorithm. Smaller values of APES result in higher accuracy but may increase the computational cost. Maxiter. This parameter sets the maximum number of iterations to run the LAS algorithm. This can be used to limit the time taken for the algorithm to run. Uncertainty methods. Bootstrap. Generate multiple bootstrap samples of the data and fit the LAS model to each sample. The variability in the coefficient estimates across the bootstrap samples can be used to estimate the uncertainty. Cross-validation. Use cross-validation to evaluate the model performance on unseen data. The variability in the performance across the different folds can be used to assess the uncertainty. Challenges and fixes. Challenge 1. High dimensionality. When the number of features is very large, the LAS algorithm can become computationally expensive. Sample use case. A dataset with millions of features. Fixes to challenge 1. Feature selection. Use feature selection techniques to reduce the number of features before running LAS. Random sampling. Use random sampling to select a smaller subset of features for LAS. Challenge 2. Collinearity. When there is high collinearity among features, the LAS algorithm may be unstable. Sample use case. A dataset with several features that are highly correlated. Fixes to challenge 2. Regularization. Use a regularization technique, such as lasso or ridge, to reduce the impact of collinearity. Principal component analysis. PCA. Apply PCA to reduce the dimensionality of the data by transforming the features into a set of uncorrelated components. sklearn, linear model, LAS pathgram. Description. The LAS least angle regression algorithm is a method for finding the solution path of the lasso problem. It is an efficient algorithm that can be used to solve problems with a large number of features. This function computes the LAS path using the Gram matrix, which is a matrix of inner products between the features. The Gram matrix is used to speed up the computation of the LAS path. Inputs. X. The training data. This should be a 2D array of shape n samples. N features. Y. The target values. This should be a 1D array of shape n samples. Outputs. Alphas. The different values of the L1 penalty parameter. Active. The indices of the features that are currently in the active set. Coefs. The coefficients of the features for each value of the L1 penalty parameter. Niter. The number of iterations taken to compute the path. Intercept. The intercept of the model for each value of the L1 penalty parameter. Dual-core. The dual coefficients for each value of the L1 penalty parameter. N features in number of features seen during fit. Feature names and names of features seen during fit. Defined only when X has feature names that are all strings. Steps. The algorithm starts with an empty active set and the coefficients set to 0. It then iteratively adds features to the active set, one at a time, by choosing the feature that is most correlated with the current residual. The algorithm continues adding features to the active set until all features have been added, until a stopping criterion is met. Metrics. Mean squared error. The mean squared error of the model on the training data. R squared. The R squared of the model on the training data. Visualization plots. The loss path can be visualized as a plot of the coefficients versus the L1 penalty parameter. The plot can be used to identify the features that are most important for the model. Fine-tune parameters. Gram precomputed gram matrix XX. XY precomputed dot product of X and Y XY. Epsilon the stopping tolerance for the LAS algorithm. Maxiter the maximum number of iterations to run the LAS algorithm. Uncertainty methods. Bootstrapping. The bootstrapping method can be used to estimate the uncertainty of the LAS path. Cross-validation. Cross-validation can be used to select the best value of the L1 penalty parameter. Challenges and fixes. Challenge 1. The LAS algorithm can be slow for large datasets. Sample use case that resulted in challenge 1: training a LAS model on a dataset with millions of samples and thousands of features. Fixes to challenge 1: the gram matrix can be precomputed to speed up the computation of the LAS path. Challenge 2: the LAS algorithm can be sensitive to the choice of the L1 penalty parameter. Sample use case that resulted in challenge 2: using a LAS model to predict the price of a house. But the chosen L1 penalty parameter results in a model that is too complex. Fixes to challenge 2: cross-validation can be used to select the best value of the L1 penalty parameter. YAML. sklearn. Linear model. LaSSOpath. Description: the LaSSOpath function in scikit-learn sklearn is used to compute the regularization path for the LaSSO model. It finds a sequence of models with decreasing values of the regularization parameter alpha and provides the corresponding coefficients for each model. Inputs. X. This is the training data. A 2D array with shape n samples. N features. Each row represents a sample, and each column represents a feature. Y. This is the target variable. A 1D array with shape n samples. It contains the values you want to predict. Outputs. Coefficients. This is a 2D array with shape n features. N alphas, where n alphas is the number of regularization parameters used. Each column represents the coefficients of the LaSSO model for a given alpha value. Alphas. This is a 1D array with shape n alphas, containing the regularization parameters used for computing the coefficients. Dual gap. This is a 1D array with shape n alphas, representing the duality gap for each alpha value. It measures the difference between the primal and dual solutions of the LaSSO optimization problem. Steps. The LaSSOpath function iterates through a range of regularization parameters alphas. For each alpha value, it solves the LaSSO optimization problem, which minimizes the sum of squared errors SSE subject to a constraint on the L1 norm of pay. Coefficients. The function returns the coefficients, alphas, and dual gap for each alpha value. Metrics. Mean squared error MSE. This measures the average squared difference between the predicted values and the actual target values. Lower MSE indicates a better fit. R squared. This measures the proportion of variance in the target variable that is explained by the model. A higher R-squared value indicates a better fit. Visualization plots. Coefficient path plot. This plot shows how the coefficients of the lasso model change as the regularization parameter alpha decreases. It helps visualize the feature selection process and identify important features. MSEVS. Alpha plot. This plot shows how the mean squared error MSE of the model changes as the regularization parameter alpha decreases. It can be used to identify the optimal alpha value that balances model complexity and performance. Fine-tune parameters. Alpha. This parameter controls the strength of the regularization penalty. A higher alpha value leads to stronger regularization and sparser models. Fit intercept. This parameter controls whether to include an intercept term in the model. Positive. This parameter controls whether to constrain the coefficients to be non-negative. Precompute. This parameter controls whether to precompute the Gram matrix, which can speed up computation. Uncertainty methods. Cross-validation. This technique can be used to estimate the uncertainty of the model predictions. It involves splitting the data into multiple folds, training the model on a subset of the data, and testing it on the remaining folds. Bootstrap. This technique involves resampling the data multiple times with replacement and training a separate model on each resampled dataset. The variability of the model predictions across the different resampled datasets can be used to estimate the uncertainty. Challenges and fixes. Challenge 1. High dimensionality of data can lead to slow computation and difficulty in finding an optimal solution. Sample use case that resulted in challenge 1 when working with datasets with thousands of features. The lassopath function can become computationally expensive. Fixes to challenge 1. Feature selection before applying lassopath. Perform feature selection to reduce the number of features. Precompute Gram matrix. Set the precompute parameter to true to precompute the Gram matrix, which can speed up computation. Use a more efficient algorithm. Explore using more efficient algorithms like the coordinate descent algorithm. Challenge 2. Choosing the optimal regularization parameter alpha is crucial for model performance. Sample use case that resulted in challenge 2 when selecting a very small alpha. The model might overfit the training data and perform poorly on unseen data. On the other hand, a very large alpha might lead to underfitting. Fixes to challenge 2. Cross-validation. Use cross-validation to estimate the performance of the model for different alpha values and select the alpha value that minimizes the error on the validation set. Grid search. Use grid search to evaluate the model performance over a range of alpha values and select the best performing one. Challenge 3. The lassopath function assumes that the target variable is continuous. Sample use case that resulted in challenge 3 when working with categorical target variables. The lassopath function is not suitable. Fixes to challenge 3. 1. Hot encoding. Convert the categorical target variable into numerical variables using one hot encoding. Use a different model. Consider using a different model like logistic regression for categorical target variables. sklearn, linear model, orthogonal MP. Description. The orthogonal matching pursuit OMP is a greedy algorithm for sparse signal recovery. Used in compressed sensing, it attempts to find the sparsest solution to a linear system of equations. Inputs. X a 2D array of shape n samples. N features representing the design matrix. Each row corresponds to a sample, and each column corresponds to a feature. Y a 1D array of shape n samples. representing the target values. Outputs. Coa A1D array of shape n features, representing the estimated coefficients of the sparse solution. Nit is an integer indicating the number of iterations the algorithm ran before converging. Steps. Initialize the coefficient vector to all zeros. Iterate until the stopping criteria are met. Calculate the residuals between the predicted and actual target values. Find the feature that is most correlated with the residuals. Add the corresponding feature to the support set. Update the coefficient vector using least squares regression on the selected features. Metrics. Mean squared error MSE measures the average squared difference between the predicted and actual target values. R squared measures the proportion of the variance in the target values that is explained by P. Model. Visualization plots. Scatter plot of the predicted vs. actual target values. Bar plot of the estimated coefficients. Highlighting the non-zero coefficients. Fine-tune parameters. N non-zero coefs, the maximum number of non-zero coefficients to allow in the solution. Toll the tolerance for the stopping criteria. Precompute whether to precompute the Gram matrix of the design matrix. Uncertainty methods. Bootstrapping repeatedly sample with replacement from the data and fit the model to each sample. To estimate the uncertainty in the coefficients. Challenges and fixes. Challenge 1. The OMP algorithm can get stuck in a local minimum, leading to a suboptimal solution. Sample use case that resulted in challenge 1. A highly correlated design matrix with a sparse signal. Fixes to challenge 1. Increase the number of iterations. Use a different initialization for the coefficient vector. Challenge 2. The OMP algorithm can be sensitive to noise in the data. Sample use case that resulted in challenge 2. Noisy measurements of the signal. Fixes to challenge 2. Use a robust regression method to handle outliers. Use a regularization technique to penalize large coefficients. sklearn, linear model, orthogonal MP-gram. Description. Solves n targets orthogonal matching pursuit OMP problems. This is the gram version. It is faster when n targets or n features is very large. Solves arm in Y, x beta 2 subject to beta 0 n non-zero coefs. It is meant to be used with the fit method. Inputs. X ND array of shape n samples. N features. Design matrix. Y ND array of shape n samples. Or n samples. N targets. Target vector or array. N non-zero coefs int. Desired number of non-zero entries in the solution. Gram ND array of shape n features. N features. D-type float. Precomputed gram matrix XTX. Outputs. Coa ND array of shape n features. Or n features. N targets. Coefficients of the OMP solution. If n targets is 1, the output is a 1D array. Nit is ND array of shape n targets. Number of active features across every target. Steps. Compute the gram matrix XTX if not given. For each target, initialize the active set to the empty set. For each iteration, find the feature with the highest correlation with the residual. Add the feature to the active set. Solve the least squares problem using the active set of features. Update the residual. Stop when the number of active features reaches n non-zero coefs. Metrics. Mean squared error MSE between the predicted and actual values. R-squared score, which measures the proportion of variance explained by the model. Visualization plots. Scatter plot of the predicted vs actual values. Residual plot, showing the difference between the predicted and actual values. Fine-tune parameters. N non-zero coefs, the number of non-zero coefficients to use in the solution. This parameter controls the sparsity of the solution. Uncertainty methods. Bootstrap aggregating bagging can be used to estimate the uncertainty in the coefficients. Challenges and fixes. Challenge 1. The number of non-zero coefficients may be too high or too low. Sample use case that resulted in challenge 1. When n non-zero coefs is too high, the model may overfit the data and have poor generalization performance. Fixes to challenge 1. You can use cross-validation to find the optimal value for n non-zero coefs. You can also use regularization techniques, such as L1 or L2 regularization, to reduce the number of non-zero coefficients. Challenge 2. The Gram matrix may be singular. Sample use case that resulted in challenge 2. This can happen when the features are highly correlated. Fixes to challenge 2. You can use a regularization technique, such as ridge regression, to prevent the Gram matrix from becoming singular. You can also select a subset of features using feature selection techniques. sklearn, linear model, ridge. Description. Ridge regression is a linear model that adds a penalty to the sum of the squared coefficients. This penalty helps to prevent overfitting by shrinking the coefficients towards zero. Ridge regression is particularly useful when there is high collinearity among the predictor variables, as it helps to stabilize the model and reduce variance. Inputs. X a 2D array of predictor variables, where each row represents a sample and each column represents a predictor variable. Y a 1D array of target values. Alpha, a float value representing the regularization strength. A higher value of alpha implies a stronger penalty on the coefficients. Fit intercept, a Boolean value indicating whether to fit an intercept term to the model. Normalize, a Boolean value indicating whether to normalize the predictor variables before fitting the model. Copix, a Boolean value indicating whether to copy the input data before fitting the model. Maxiter, an integer value representing the maximum number of iterations to perform during model fitting. Toll, a float value representing the tolerance for the stopping criterion. Solver, a string value representing the solver used for model fitting. Random state, an integer value representing the seed for the random number generator. Outputs. Core a 1D array containing the estimated coefficients for each predictor variable. Intercept, a float value representing the estimated intercept term. Steps. The model first initializes the coefficients and intercept term. The model then iteratively updates the coefficients and intercept term to minimize the loss. Function, which includes a penalty term based on the sum of squared coefficients. The model continues to iterate until it reaches a stopping criterion, such as a maximum number of iterations or a tolerance level. Metrics. Mean squared error MSE, a measure of the average squared difference between the predicted values and the actual values. R squared, a measure of the proportion of variance in the target variable that is explained by K. Predictor variables. Mean absolute error may, a measure of the average absolute difference between the predicted values and the actual values. Visualization plots. Scatter plots of the predicted values vs the actual values. Residual plots to check for any patterns in the errors. Coefficient plots to visualize the magnitude of the coefficients for each predictor variable. Fine-tune parameters. Alpha, regularization strength. Higher values lead to stronger shrinkage and reduce variance but can increase bias. Use cross-validation to find the best value. Fit intercept, whether to include an intercept term in the model. Typically included unless the data is centered. Normalize, whether to normalize the predictor variables. Can improve performance if the variables have different scales. Uncertainty methods. Confidence intervals for the coefficients can be obtained using bootstrap resampling. Prediction intervals for new data points can be obtained using bootstrap resampling or Bayesian methods. Challenges and fixes. Challenge 1 overfitting. Sample use case that resulted in challenge 1 using a high number of features with a small amount of data can lead to overfitting. Fixes to challenge 1 use a regularization technique like ridge regression to shrink the coefficients towards 0 and reduce overfitting. Challenge 2 multicollinearity. Sample use case that resulted in challenge 2 when multiple predictor variables are highly correlated. This can lead to unstable estimates of the coefficients. Fixes to challenge 2 use ridge regression, which adds a penalty to the sum of squared coefficients and helps to stabilize the estimates. Challenge 3 scaled features. Sample use case that resulted in challenge 3 if the predictor variables are not scaled. The model can be sensitive to the scales of the variables. Fixes to challenge 3 normalize the predictor variables before fitting the model.